Warm welcome to all. City-based course that is on Introduction to Embedded Systems department during this present week, that is from 8 to 12 February. I would like to thank all the colleges, institutes and universities for showing their keen interest to connect as nodal centers for this program. I extend a very warm welcome to all the chief guests, dignitaries at nodal centers, local coordinators, program participants at studio and at various nodal centers to be the part of this event, that is Introduction to Embedded Systems, which is run through ICT induction mode. In this course, experts have been invited from industries like SGS, Electronics, CSIU to discuss about embedded system design aspects and to give exposure to Android platform for the designing of embedded systems. Also, experts from renowned academic institutes like NIT, PEC, UIT, Chandigarh have also been invited to give an idea about embedded systems, their applications in service robots, biomedical field, wireless sensor network, and the Arduino microcontroller, and the role of this Arduino microcontroller in the development of embedded system applications. I hope for fruitful interaction of our participants with our experts. So now I request local coordinators of all the centers to kindly introduce their respective chief guests. So to start with, we have Professor Arun Chopra, who is acting as local coordinator for JECRC Jaipur. Hello, Professor Arun Chopra from at present who is connected with us? Okay, Professor Arun Chopra from JECRC Jaipur. Sir, am I audible to you? Professor Arun Chopra. Sir, am I audible to you? Okay. Then Professor Anush Sharma from DIT University, Dehradun. Coordinator from PVP Siddhartha, Andhra Pradesh.
Good morning, madam. Good morning from.
Good morning, sir.
Yeah, I'm Krishna Prasad, coordinator for here Knowledge Center. So.
Please introduce your chief guest.
Yeah.
Myself, I'm Srinivas Rao, associate professor here. We are expecting the in-detail analysis of these embedded systems, Android platform, and ARM processor. We are eagerly waiting for your lectures.
So I hope for fruitful interaction of all the participants at Andhra Pradesh with our experts.
Yes, madam.
Yeah. So thank you PVP Siddhartha College. Now next, we should call upon Professor Anush Sharma from DIT University, Dehradun. Then Professor Manish Mehta from JCTM College of Engineering, Sirsa, Haryana.
Good morning, NITTRCHD.
Good morning, sir.
Yeah, good morning, Professor Sharma and all the team members. So first of all, I would like to thank NITTRCHD and the whole technical team for giving us an opportunity to join with you and to see and to watch and to learn embedded system course. So we have faculty members of Electronics and Communication Department, few MTech students, few research scholars are there, as well as faculty from the Computer Science Department. So hopefully from the for next 5 days we will find betterment in embedded system. We will learn about the embedded system, and same thing we can pass on to our learning graduates, BTech graduates. And thank you very much, sir, and ma'am. Thank you, the whole team. Thank you.
Okay, thank you, sir. Thank you. Now next, Shri A.K. Moel from TTC Jodhpur. Shri A.K. Moel from TTC Jodhpur. Sir, kindly introduce your chief guest. Okay. Then next, Dr. Richa Yadav, who is acting as a coordinator for IGDTU, Delhi. Ma'am, please introduce your chief guest.
Good morning, ma'am.
Good morning.
Our chief guest is Dr. Jaspreet Kaur, HOD Electronics Department.
Okay, ma'am. Please go ahead.
On behalf of organizing committee, it is my pleasure to welcome you all in this FTP program on Introduction to Embedded Systems. This program is conducted by Department of Electronics in collaboration with Mr. Chandigarh. Last October also, our department had organized similar program with NITTTR. That was really a pleasant and beneficial experience. It is our great pleasure and privilege to have this opportunity once again. This FDP will be beneficial for the participants and helps in cultivating new thoughts in the field of embedded systems. I believe that all of you will have a pleasant experience and this program will add to your practical knowledge base. With this hope, I once again extend a warm welcome to all our participants and thank them all for being part of this program. I would also like to take this opportunity to thank our Honorable Vice Chancellor, Professor Nupur Prakash, for giving us the privilege of hosting this program. I hope the confidence placed in us by VC ma'am will be justified by efforts of our organizing team. I sincerely thank our respected HOD ma'am for her support and for accepting our invitation to be with us this morning. Her encouragement is really valuable. Thank you once again.
Thank you, ma'am. Now next center is Northern India Engineering College. Yeah, Dr. Rajiv Sharma. Sir, kindly
Kanika
introduce
Sharma.
our chief guest. Yeah.
Hello,
Hello.
am I audible?
Yes, sir. You are audible. Please
Good
go
morning,
ahead.
Dr. Kanika Sharma.
Good morning, sir.
From Northern Engineering College, on the behalf of the institute, first of all, I'd like to thank NITTR for including us for this program. And the chief guest of this morning session is our director, Dr. G.P. Govel. So I'm going to request our chief guest, Dr. G.P. Govel, to say a few words.
Good morning, madam.
Good morning, sir.
Hello. Yeah. First of all, I must thank NITTTR Chandigarh to have such programs where they are highly interactive, informative, and really motivates our faculty who are attending this on the regular basis. So I wish all the best, and I'll be here to listen to that and convey my regards to Dr. Punia also. We were together at IIT Delhi. Okay. I think wish you all the best. Thank you.
Okay, sir. Okay. Thank you, sir. Thank you. Thanks a lot. Albert. Yeah. Introduce the next coordinator, who is Mr. Kumar Sharma, acting as local coordinator for the Institute of Engineering and Technology, Alwar. Sir, kindly introduce your chief guest.
Hello. Am I audible?
Yes, sir. You are audible.
Yes, ma'am. Good morning to all, and I really thanks first of all to you for organizing such a event. And from our side, our guest is Dr. V.K. Nasa from Masari University. And here we have various faculties from the various departments to gain out of this session. Thank you. Hello.
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 Hello. Yes, sir. Please go ahead.
Yes, ma'am. Good morning, ma'am. I'm S.K. Bhavna from IT Elder. And today we have our chief guest, Dr. V.K. Nasa from Masari University. And we are looking forward to gain out of this session. Thank you.
Okay, sir. Thank you. Thank you. Professor Arun Chopra from JECRC Jaipur. Sir, kindly introduce your chief guest, JECRC Jaipur. Is this center is connected? Yes, Professor Arun Chopra. Professor Arun Chopra from JECRC Jaipur. Other centers which are in. Okay. So I hope that there should be a fruitful interaction of our participants with our experts. So we will come again and join at 11:30 after a tea break. Okay, thank you.
Hello. Hello, can I able to hear? Hello, Param. Hello.
Maybe also center.
हेलो यस सर
हाँ सर एक ना शेड्यूल नहीं कर दो सर
शेड्यूल
So for the first day, that is on today itself, at 11:30 we have a session on embedded system design aspect, which is taken up by Mrs. Sharmili, who is acting as HOD of that UIT in Electronics and Communication Department. And
it's a first session.
pardon, sir?
It is in the first session, huh?
Yeah, this is the first session which will begin at 11:30 and it will move up to 1 p.m.
Okay, 11:30 to 1.
1 p.m. It's for 1 and 30 minutes. 1 hour and 30 minutes. The session will be of for 1 hour 30 minutes. And this session will be taken up by Mrs. Sharmili, who is acting as C department in UIT Chandigarh. In the afternoon, we have a session from 2 to 4 p.m. That this session is about the
You
Android
are not audible. I'm sorry.
Android platform which is used for embedded systems.
Sorry, you are not audible. If you can mail the whole.
I have already emailed the this course contents along with the timetable of this short-term course.
So, ma'am, by if you can again mail it. Sorry, you are not audible. If you can again email the whole content.
Okay. I will again email this timetable to the center.
Yeah. Okay, thank you very much.
Okay. So we will meet again at 11:30. Our first session of this course will begin at 11:30. So we'll come after the tea break at 11:30 in this studio. Okay, thank you. Thanks a lot. Connected at DIT Dehradun. Okay, hello. Is this DIT Dehradun is connected? Am I audible to DIT?
Yes, ma'am.
Yes, Professor Anuj Sharma. Hello.
Yes, ma'am. Yes, ma'am. You are
Yes,
audible.
Anuj Sharma.
Hello.
Yes, you are audible. Please
Yes,
introduce
ma'am.
the chief guest.
Yes, yes.
Yes.
Hmm? No, ma'am. No chief guest at our end.
Okay, then you can inaugurate your session at your center only.
Okay, ma'am. Yes, ma'am. Ma'am, it's a wonderful opportunity to join NITTTR for this course. We have earlier also joined some courses, so it was a wonderful experience, and we are hoping that this time also we are having a good experience over this embedded system.
Okay, okay. Thank
Am I
you, sir.
audible?
Yes, sir. Yes, you are
Okay.
audible. So we will again meet at 11:30. Our first session will start at 11:30 only.
Okay.
Okay. Thank you, sir.
Okay,
Thank you.
fine.
Okay.
Hello, Bana Bhe. Kalau nama itu dia nama ini body table का तो हम क्या हो गया मतलब ऐसा नहीं तभी सही लगता वो याद आता क्या बोला हम बिना बोला था फिर हम बोलेंगे ये ऐसा फिर ऐसा mana ada tuh di London tuh tinggal gini ya tinggal gini itu dia bosan kalau lagi di भाग नहीं चाहिए
ऐसे जो एक्सटेंशन कोड है सर
ये भी है हमारे पास
सर बच्चे लैपटॉप पे यूज करेंगे लैपटॉप पूरे दिन 6-7 घंटे तो नहीं चलेगा सर कुछ हो सकता है बताओ सर
एक्सटेंशन ये लग तो रही है इसमें
नहीं इस तरह का बैठे
हैं
इस तरह सेंटर में जो बैठेंगे ना बच्चे सर
इसको सॉल्व मिल जाएगा
ये फोन कर लो यहाँ से फ्री सेवा है। हाँ फ्री सेवा कर दिया इसका सर्वर उनका उसका है 7 कुछ था।
आपका मतलब 1/7 तो बोला ना।
हाँ 1/5
हमें लिखना दो हमें ये इनका पता नहीं ये हमारी टीचर इनका भाई है यहाँ देख लो बस ऐसा हमारा
वो लगा तो वो पंची जो वहां लगी
है
वो स्लिप जो वहां लगी वो बाहर तो लगा तो एक
बाहर को जरूरत नहीं पड़ती वो अंदर ही जरूरत पड़ा।
हेलो हाँ सर मुझे जैन जी से बात करनी थी।
अब यहाँ बैठ के वो लगाओ वहां से लास्ट में वो बीच में पड़ेगा
मेरा लगेगा पासवर्ड
क्या करेगा क्या
ये क्यों नहीं चल रहा है लो अभी चल गया था ना चला था ना पांडे चाय मंगा लो फिर चाय मंगा लो पांडे सर चाय मंगा लो क्या
चल रहा है दवाई
घंटा क्लास में गया था ठीक है 10 मिनट लगातार पढ़ा लूंगा 10 मिनट पढ़ाओ नीचे में रख दो 10 मिनट पढ़ाओ 10 मिनट पढ़ाओ उनकी बात तो देखी ना अब क्या करें मुझे अटेंड करवा दो हाँ वो करवा रहे वो विनोद जी वो
बताइए सर मनाली गया
मनाली क्या
इसका क्या क्वार्टर लो
कुछ अंदर कराए ना नहीं हम जा रहे बनाने नहीं ये भी देखते हम क्या पक्का में ये बात देखने जा रहे हैं वो ले जाते थैंक यू एक ऐसा घर आएगा जब सबको दे रखे सब और 10 को दे रखे फिर भी आइए जैसा हम इसी काम करते हैं last line में लेगा तो आधा लास्ट लाइन में हाफ इधर से डिवाइड हो जाओ सर कॉपी कितनी बनानी
प्रोग्राम चल रहा है वो भी चाहिए डिपार्टमेंट में
दस पेटी है सर अभी कुछ नहीं सर बेकरी वाले हैं ना बेकरी वाला ये मसाला लिखा हुआ बिजू सर ना एक मिनट आगे बढ़ते अपन सेम नाम लिखी हुई बोले से फिर दबाएंगे हमारे जगह नाम हमारे नाम बोलो आगे कंप्लीट हां तो एनर्जी मैनेजमेंट का तो हम इधर करेंगे और उधर करेंगे आप देखिए सर्टिफिकेट नहीं आया जी यहाँ करो अरे दोनों का
गिफ्ट बहुत देते थे अभी होली का आसत है
हाँ एनर्जी इसलिए तो मैंने लिया नहीं लेकिन ये था आपको नंबर भी नहीं आता मेरा नाम रजिस्टर्ड है डायरेक्ट ऑफिस बस नहीं करता
चलो शुरू करते हैं होली का एक बात
हाँ उसके बाद
शुरू
क्लास में उसको मेट्रिक क्लास में मैं उनकी अभी उन्हीं की क्लास में था हाँ ये एम्बेडेड सिस्टम का एक कोर्स चल रहा है आप लोग बैठ सकते हो पीछे बैठ जाओ नहीं नहीं अभी सर सर इसको हाँ हाँ चल रहा है अभी बस स्टार्ट होने वाला है ये पता नहीं देखो चल रहा है ना टी ब्रेक खत्म होने वाला है 15 मिनट तो ये इसमें लगवा देंगे तो दूसरे नहीं 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 समझा कोई भी कनेक्ट करना मुश्किल हो
I welcome you once again. Uh, Now we have amongst us our next speaker. She is Sharmili Thangjam. She is working as head of the department in EC department at UIT Chandigarh. She has a teaching experience of 12 years in UIT PU Chandigarh, and her research areas are signal processing, communication, and embedded system. She has guided a number of ME and MTech theses in the area of and she has also developed a research project named as Low Power DSP Lab under grant received from AICT. So I welcome you, ma'am, in this session, and now I hope that there should be a fruitful interaction of all with our expert. So over to you, ma'am.
Good morning to all the participants. I'll be talking on embedded system design aspects. So I'll be starting with introduction, then we'll go on to the various aspects of embedded system design. Full screen.
You just have to press this button.
Okay, so I'll be talking about the embedded system design aspects. Before we start with the actual embedded system design, let's see what is the definition of a system. So a system is a way of working, organizing, or performing one or many tasks according to a fixed set of rules, program, or plan. It is also an arrangement in which all units assemble and work together according to a program or a plan. Examples of systems are, for example, you have a time display system like a watch, an automatic cloth washing machine washing system. Some certain definitions of embedded systems according to different experts. Some of the definitions are: an embedded system is a system that has software embedded into a computer hardware, which makes a system dedicated for an application or a specific part of an application or a product or a part of a larger system. It is also one that has a dedicated purpose software embedded in a computer hardware. It is also a dedicated computer-based system for an application or product. It is an independent system or a part of a large system. It is the software is usually embedded into a ROM, that is a read-only memory, or a flash. It is also any device that includes a programmable computer but is not meant for a general purpose application. It is meant for a specific application. These are also electronic systems that contain a microprocessor or a microcontroller, but we do not think of them as computers. That is, the computer is hidden or embedded in the system. Now, for example, let's consider a general purpose computer. It has the following components like a microprocessor, a large memory comprising the following two kinds of memory. That is, you have your primary memory, you have your secondary memory. Then you have input units such as your keyboard, mouse, digitizer, scanner. Then you have your operating system. Then general purpose user interfaces and application software, mostly in the secondary memory. Now, when we talk about an embedded system, we've just seen what a general purpose computer looks like. When we talk about an embedded system, there are three main embedded components. The first thing is it embeds hardware to give computer-like functionalities. Certain hardware is embedded in the system. Then it embeds certain main application software, generally into the flash or the ROM, and the application software performs concurrently a number of tasks. And these tasks are all application specific. Then the third thing is it embeds a real-time operating system. Okay, so in case of an embedded system, we have what is known as your real-time operating system, which supervises the application software task running on the hardware and organizes the accesses to system resources according to priorities and timing constraints of tasks in the system. Now, what is this real-time operating system? Briefly, I think this will be taken up in the later lectures, but just to give you a brief overview. This real-time operating system, it enables execution of concurrent processes or threads or tasks that are running concurrently. It provides a mechanism to let the processor run each process as per the scheduling. The processes are scheduled, so as per the scheduling, and do context switch between the various processes, threads, or task context switching. Then real-time operating system also sets the rules during execution of application process to enable finishing of a process within the assigned time interval and with the assigned priority. So you have different tasks with different time intervals and assigned priority. The real-time operating system manages all these tasks and processes. This we can skip this. Sophisticated embedded system characteristics. Certain characteristics, that is, we have in an embedded system, we have dedicated functions, we have dedicated complex algorithm, because these are all application specific. It's not general purpose. Then you have dedicated graphical user interface and other interfaces for the application. Then you have these real-time operations. This operation defines the ways in which the system works, reacts to events and interrupts, schedules the system functioning in real time. That is, your processes are functioning in real time, and executes by following a plan to control the latencies and to meet the deadlines. Then you have multi-rate operations. Different operations may be taking place at different rates. Okay, different rates. For example, you can have audio, video, network data, or stream and events have different rates and time constraints to finish the associated processes. So multiple operations running at different rates. There are certain constraints of an embedded system design. When we design an embedded system, there are certain constraints which we do not face when we go in for a general purpose system design. So the first constraint is available system memory. How much is the memory available to you on chip? Then how much external memory that you require to put in. Then the available processor speed, depending upon your application, you see which processor is suitable for your particular application. Limited power dissipation when running the system continuously in cycles of the system start, wait for event, wake up, sleep, run, sleep, and stop. So power dissipation should be kept at the minimum. Then performance, constraints of performance, power, size, non-recurring design cost, manufacturing cost. So these are some of the constraints we face when we design embedded systems. So now that was a brief overview of embedded systems. Now let's come to the second part, in which we have a look at the different processors and embedded system for what type of an application you select a particular processor. Now before that, let's have a look at the hardware units in the embedded system. The hardware units, you have the power supply, reset and oscillator circuits. Then you have input devices, interfacing, driver circuits. You have your processor, timers, interrupt controller, program memory and a data memory, serial communication ports, parallel ports, output interfacing, driver circuits. Then you have system application specific circuits, which is for that particular application. Okay, now the processor consists of two main units, that is your program flow and the data path control unit. This part includes a fetch unit for fetching instructions from the memory. Then you have your execution unit, which includes the circuits for arithmetic and logical unit, and for instructions for program control task. Say, for example, your data transfer instructions, halt, interrupt, jump to another set of instructions, or call to another routine, or sleep or reset. Now, there are certain considerations that a system designer, an embedded system designer, has to take into consideration. The first one is when you're selecting a processor. That is, the processor instructions in the instruction set are all the instructions applicable for your particular application. Then the processor ability to solve complex algorithms used in meeting the deadlines for their processing. The maximum bits in the operand, that is, whether in a single arithmetic or logical operation you have an 8-bit operand or a 16-bit or a 32-bit. Then the internal and external bus widths in the data part. An internal bus width, what is the width of the bus, whether it's a 8-bit bus or a 16-bit bus or a 32-bit bus. Then the clock frequency in megahertz and the processing speed. So the clock frequency, the processing speed you measure in millions of instructions per second or millions of floating point instructions per second. You have another benchmark. This is a dry stone. This is a benchmarking program for excuse me, measuring the processing performance. So these are various benchmarks through which you measure your processing speed and the clock frequency. So this is one thing that we have to keep in mind while designing an embedded system. Now, when we select these different processors meant for an embedded application, there are certain processors, microprocessors, microcontrollers, or a specific application processor that we can select. So the first one, you can either go in for a general purpose microprocessor like Intel 8086, SPARC, or Motorola 68HC XXX family. Or you can go in for an embedded general purpose processor. Embedded general purpose processor. This gives you fast context switching features like use of on-chip compilers. For example, an example of this embedded general purpose processor is your Intel Xscale. Okay, then the second type, you can have an application specific instruction set processor. Application specific instruction set processor. For example, you have microcontrollers from Intel, Motorola, Hitachi, Texas Instruments, Philips, and ARM. So you can have 8051, Philips 51XA, 51MX series, Motorola 68HC11, 68HC12, 68HC16. These are all application specific instruction set processor. Then some microcontrollers which are used in small scale embedded system. When you are a design on a small scale, you can either go in for an 8 or a 16-bit microcontroller like you have from the 8051 family or the PIC16FX series family, the Hitachi H8 family, the 68HC11 XX family. Okay, these are used in small scale embedded system. Then when we go in for a medium scale embedded system, we go in for 16-bit microcontroller like 8051MX family, PIC16F876, PIC18, Hitachi D64F2623FA, 68HC12XX, 68HC16XX. So these are used in medium scale embedded system design. Then in large scale embedded system, when you go in for a high-end system, we go in for 32-bit microcontrollers from the ARM family, the Cortex M3, Atmel 8091 series, the ST10 series, Philips LPC 2000 series, Texas Instruments C16, and TMS 470R1B1M, Samsung S3C44BOX. Then you have from the Hitachi SH7045F. So these are 32-bit microcontrollers that we use in large scale embedded system. Okay, this is not very visible. Okay. Then we can also go in for application specific instruction set processor. Application specific instruction set processor, like the second part. For the first one was your microcontrollers. The second one, you have your DSP processors. digital signal processors, or media processor, or an I/O processor, or a network processor, or a domain-specific processor. So these are all application-specific instruction set processors. So you can, depending on your application, you can select any of these processors. So DSP processors, digital signal processing, meant for digital signal processing applications, like if you want to incorporate a MAC unit in your embedded system design, you go in for a DSP processor. So you can have from the Texas Instruments C28X family, C54, C64, or you can have from Analog Devices, the Shark or the Tiger Shark family of DSP processors, or Motorola 5600XX series. Then you can also go in for a media processor. If you have lots of processing, video processing, speech processing, and so on, you can go in for a media processor like the one from Texas Instruments, TMS320DM310, or Trimedia Philips media processor, 1x00 series for processing, streaming, and data network, and image, video, and speech. Okay, so these media processors are meant for this image, video, speech type of application. Then you can go in for a general purpose processor, or an applications specific IP core. So in this, general purpose processor, or an application specific integrated processor, is integrated into either an application specific integrated circuit, or a VLSI circuit, or an FPGA core integrated with the processor unit in a VLSI ASIC chip. Okay. Now, then you can also have an application specific system processor. So this is typically if you want to speed up your processor, fast processing you require, you go in for this application specific system processor. So typically in this type of processors, you have a set-top box processor, or a MPEG video processor, or a network application processor, or a mobile application processor. So this is application specific. Then you can have a single purpose processor, or an application specific instruction processor. Single purpose, which is meant only for a single purpose. For example, you have a floating point coprocessor which will work with your floating point operations, a CCD pixel coprocessor, an image codec in a digital camera, a graphic processor meant only for graphical applications, a speech processor, adaptive filtering processor, so on. Encryption engine, a decryption engine, a communication protocol stack processor, a Java accelerator. These are all application specific processors. Okay, this we can skip. Then you can have multi-core processors, or multi-processor system using general purpose processor. That is, you have the system. So for example, you have multi-processor system for video conference system, or embedded So here we had an overview of the hardware units, the processors which are used in your embedded system design application. Now, next we come to the hardware elements in an embedded system. Okay, so again we have seen the hardware elements, we had a look at the processors. Now let's come to the next one, that is the basic circuit elements in the system. The first element is your power source. So power source can be of two types. The system owns supply with separate supply rails for IOs, clock, basic processor, and memory and analog units, or you can have supply from a system to which the embedded system interfaces, for example in a network card, or you can have charge pump concept used in system of little power needs. That is, when your power needs are very less, power requirements are less, you have charge pump concept where you have diodes and capacitors which charges through your wireless radiation and so on. For example, in your mouse or contactless smart card. So these are different types of power sources you can have. Then you need to manage the power dissipation also. Okay, so how do we do that? By clever real-time programming, by wait and stop instructions, by clever reduction of the clock rate during specific set of instructions. Specific set of instructions reduces your clock rate, optimizing your codes, and clever enabling and disabling of use of caches and cache blocks. Then the clock oscillator circuit and the clocking unit. So this is the second part. We had to look at a power source. Next is your clock oscillator circuit and the clocking unit. So here you have an appropriate clock oscillator circuit. Then you have real-time clock or a system clock and timers driving hardware and software. Then you have your reset circuit. Reset circuit is reset on power up. Then you have external and internal reset circuit. Then you can also have a reset on timeout of watchdog timer. Okay, so embedded system design, you'll be coming across watchdog timers. This type of timers are useful when you are when the system is stuck or hung. It gives certain timeout to the processor. So after that certain timeout, it resets your system. Okay. Then we come to the memory unit. There are different forms of system memory. You have the internal RAM, which is inside your microcontroller. I think it's not very visible. Then you have the RAM at the system on chip or the external RAM. Then you have internal caches at the microprocessor. Then you have external RAM chips. Then you can have flash, EEPROM, PROM, and ROM, which is external or internal. Then you have memory addresses at the system port. So these are the different types of memories. Now the function assigned to the ROM or EEPROM or flash, it stores the application program from where the processor fetches instruction code. So embedded system design, that is embedded system meant for a particular specific application. So this application program is stored in your ROM or EEPROM or flash. Then the ROM or EEPROM or flash, this is also used for storing codes for system booting, initializing, initial input data and strings. It is also used for storing codes for your real-time operating system. Then it also stores pointers, or that is the address of various service routines. You have your various service routines, your pointers, and that is stored in your ROM or EEPROM. Then what are the functions that are assigned to the internal, external, and the buffer RAM? So this type of memory, they store the variables during program run. When your program is running, the variables, it stores a stack. Okay, your stack keeps changing, stack pointer. Then it stores the input or output buffers, for example, for speech or image. The function that is assigned to the EEPROM or the flash, it stores the non-volatile results of processing. Then caches, what are the functions of the caches? It stores copies of the instructions, data and branch transfer instructions in advance from external memories. Okay. Then it stores temporarily the results in write-back caches during fast processing. Okay. So cache applications ke liye you have this cache memory. Then the next hardware element is your interrupt handler. Okay, we've seen the different types of memories and where these memories are used. We come to interrupt handler. So this you have this interrupt handling element for the external port interrupts, different types of interrupts. You have different types of interrupts in your microcontrollers for this embedded application. So you have external port interrupts, I/O interrupts, timer and real-time interrupts, software interrupts and exceptions. For different types of interrupts, you have this interrupt handler. Then you have a linker which will link your embedded system hardware. So this element will link and interface a circuit for the buses by using the appropriate multiplexers, decoders, demultiplexers, and it also interfaces with various system units. Then you have this I/O communication unit. Here you have your communication drivers like your network Ethernet or the serial driver to communicate with the host embedded system. So for this you have your serial buses and parallel buses, UART, I2, CAN, SM, I2C, SPI, CAN bus, different types of buses. SCSI parallel, fast SCSI, ultra. These are different types of serial and parallel buses. Okay. Then you have the media input-output control element. Under this, you have your keyboard or the keyboard I/O interface, the LCD display system interface, the ADC, analog to digital converter, single or multi-channel, the DAC, the GPIB interface, the pulse dialing element, modem, Bluetooth, and so on. So these are different I/O elements. Okay. So here we had to look at the various hardware elements. That is your basic circuit elements like power source, clock, reset, timers, memory, the glue circuit, etc. Okay. Then next we've seen the hardware elements. Next we come to the software for embedding in the system. Okay. So you have here you have the ROM image, the programming languages, and the programming models. So let's have a look at what is this ROM image. Your final software, final stage software, that is you've written the code, the final that is intended for your specific application. This software, this is also called the ROM image. Okay. So now this system ROM memory, this will embed the software, the RTOS, the data, and the vector addresses. Okay. This has your final machine software. So this final machine software is where you have bytes at each address defined for creating the ROM image. Okay. Then by changing this ROM image nothing but your program which contains this your system software, the RTOS, the data, and the vector addresses. So by changing this image, the same hardware platform works differently and can be used for entirely different applications or for new upgrades of the same system. That is, same hardware, if you change the ROM image, that is, if you change the program, the software, you can use it for different applications. Okay. Now you have a distinct ROM image in a distinct embedded system. A particular embedded system will have a distinct ROM image. The hardware elements between the distinct systems can be identical. You can have the same hardware, but it is a software that makes the system unique and distinct from each other and makes it intended for a particular application. Your ROM image can be compressed codes and data. So ROM image may alternatively be compressed software, for example, in a zip format, or it can be data, for example, the pictures in JPG or GIF format, along with the softwares required for decompression algorithm. Then next we come to the programming languages. Okay. First you have your machine language coding. Your coding can be in machine language. Here the programmer defines the addresses and the corresponding bytes or bits at each address. Now this type of coding is used in configuring some specific physical device or subsystem like your transceiver. The machine code based here machine code based coding is used. Then we have the assembly language coding. This is needed for invoking processor specific application. Okay. This is also required for understanding of the processor and the instruction set. This requires understanding of the processor and the instruction set. So if you have to do the coding in the assembly language, you need to know the type, the particular the processor that you're using and the instruction set of that processor. A program or a small specific part coded in the assembly language using an assembler. So that becomes your assembly language code. Now there are 3 steps that is required when using assembly language. You need your assembler, linker, locator before your final code is being burned into the ROM. Okay, so this is your flow diagram. You have the machine specific assembly language program through the assembler. Then it becomes the machine codes for the program at various addresses. From the library needed machine codes, you have this is given through the linker. This gives you the bytes for the link program. Then addresses are relocated To the loader, this is given to, after relocating the addresses, this is given to as machine codes ready for loading at various address points. Now this is being burnt into the device ROM programmer using the burner. And finally, this is being embedded into the embedded system ROM memory. This is your conversion process from the assembly code to the ROM image. Then you can also have a high-level language programming language like your C or C++ or Visual C++ or Java. So these are the, when you going for this high-level language programming, these are the different program layers. You have preprocessor commands, you have main function, interrupt service routines, different tasks, the kernel and the scheduler, standard library, the functions including the network protocol, functions for sending stack and receiving stack. So these are the different layers. Okay. Then what is the function of the compiler? When you're going for high-level language programming, we need a compiler. Compiler this generates an object file using linker and locator. The file for the ROM image is created for the targeted hardware. C++ and Java are the other languages used for software coding. Now this is how we convert a high-level code, for example a C program, into a ROM image. So you have your C program functions. These are passed through the compiler, generates the machine codes in the object file. Then this is passed to the code optimizer. This generates programming models. So programming models, how you write the programs using this language, high-level language, etc. So you have the sequential programming model, you have object-oriented programming model, and you also have control and data flow graphs, or the synchronous data flow graph, or the multi-thread graph model, the finite state machine for the data part, multi-threaded model, concurrent processing of processes or threads or tasks. So these are the finite state machine. Okay, for this we can go hardware description languages like your VHDL, Verilog, and so on. Okay. Okay, so we had a look at the different programming models. Now let's have a look at how at the different softwares for embedding in the system. So first we come to device drivers. What are device drivers? Now in an embedded system there are a number of physical devices. You have physical devices like your keypad, your LCD display or the touch screen, memory stick, wireless networking device, parallel card, and so on. You have a number of physical devices. So in an embedded system, again, you have a number of virtual devices, not only physical device, a virtual device like pipe, file, RAM, disk, socket, and so on. So what is the function of this device driver? What does it do? This is a software for controlling or configuring, receiving, sending a byte or a stream of bytes from or to a device. Now, device driver can be a set of generic functions such as create, open, connect, listen, accept, read, write, close, delete, which are used by high-level programmers. So the function calls a specific software or an interrupt service routine which controls a device function or a device input or output. This also controls and functions by calling an interrupt service routine on hardware or software interrupt. When you have a hardware or software interrupt, it calls an interrupt service routine. It places appropriate bits at the control register or the word of your particular microcontroller. Then it sets up the status flag in the status register for interrupting, therefore running the interrupt service routine, resetting the status flag after interrupt service. Okay, next we come to the device manager. So device manager for the device and drivers. So you have your device management software. Usually it is a part of the operating system. This provide codes for detecting the presence of device. For initializing, you detect the presence of device. Once the device presence is detected, you initialize or configure this device and testing the device that are present. So you have this device management software. This also in software asking you operating system and real time. So processes, tasks, or threads. Now, the system is composed of two or more concurrent processes that execute multitasking software, scheduling multiple tasks, processes, memory, device, ports, network, file system. Keep several
आ रही है, आनी चाहिए.
Your digital camera, robots, point of sale term, for a robotic system, washing machine, digital panel for voltage, resistance, laser print, in a server, switch, bridge, hub, and gateway. Then in a distributed
Net.
systems, for example, embedded systems for video, interactive video, broadband, IPv6, internet, and other products. Okay, so these are the different applications of embedded systems. So everywhere we look, right from the smallest application to the most sophisticated. units, your digital and analog units. So you can embed a general purpose, can also be embedded on a VLSI chip. Application specific course, different course. This can also be embedded on the VLSI chip. Then we can embed a multiprocessor or a dual core using general purpose processors. For example, we can have speech signal compression and coding, a processor meant for this. Can also be chip. Accelerator will speed up your processing for a particular application. This will accelerate the execution of codes. For example, a floating point coprocessor. This will speed up your floating point operation. This accelerates the mathematical operations. This accelerator is also on a VLSI chip. Then we can embed single purpose processors which are meant for a single purpose. For example, for dialing, modulating, transmitting, demodulating and receiving. Then keypad interface and display interface handling, touch screen, message display and creation, SMS and MMS, protocol stack generation, pixel coprocessor and codec in a digital camera. So these are single purpose processors. This type of single purpose processors can also be embedded on the VLSI chip. So system on a chip is an embedded processor, general purpose or application specific core, or it can have single purpose processing cores or multiple processing cores, or it can have a network bus protocol core and encryption decryption function cores for FFT, fast Fourier transform, discrete cosine transform for signal processing applications, memories and so on. Then you can also have multiple standard source solution called IP cores or intellectual property. This can also be embedded. Then you can have programmable logic device and FPGA cores and other logic and analog units. What is this intellectual property, IP cores? This is a standard source solution for synthesizing a higher level component by configuring a core of the VLSI circuit or the FPGA core available as an intellectual property. So a higher level component, this is being configured as a core, and then you can as a core, an IP core. It can be either a core of the VLSI circuit or it can be an FPGA core. Then it is embedded onto the VLSI chip, so it becomes a system on a chip. Then you can also have high level components with gate level sophistication circuit much above the level of counters and registers. Now, designer or the designing company, this holds a copyright for the synthesized design of a higher level component for the gate level implementation of an IP. Okay, it holds the copyright, so it's not freely available. So one might have to pay royalty for every chip shipped. An embedded system may incorporate several IPs. So we can buy an IP core. You don't have to develop everything from scratch, readily available IP core. You can buy from a certain company, then you can embed it into your system on a chip. An IP may provide a design. Examples of IP cores. It can provide a design for adaptive filtering of a signal, the full design for implementing your HTTP protocol or a file transfer protocol, your USB port controller, Bluetooth, GPS interface, wireless interface, and so on. So you don't have to develop the code by yourself. Then what are these FPGA cores? that is your FPGA filled programmable gate array. Now this consists of a large number of programmable gates on a VLSI chip. There is a set of gates in each FPGA cell, which is called a macro cell. Embedded system designed with a view of offering enhancing functionalities in future. Then FPGA core can be used in the circuits. Okay, if you want to upgrade or if you want to enhance the functionalities, then normally we can go in for an FPGA core. So in an FPGA core, each cell has several inputs and outputs, and all the cells are interconnected like an array or a matrix. You have programmable interconnects between the cells. So each connection is programmable through associated memory RAM in an FPGA programming tool. The concept is using FPGA core along with single or multiple processors. So I use an FPGA core along with a separate processor or multiple processors. Examples of FPGAs are Xilinx Spartan 3, Vertex. Okay, these are all examples of FPGAs. This is an example. So, for example, in FPGA, using FPGA, a single instruction, multiple Fourier transform and its inverse, DSP or Laplace transform and its inverse, compression or decompression, encrypting or deciphering, a specific pattern recognition. Okay, this all can be implemented using your FPGA, and you can configure an algorithm into the logic gates of the FPGA. These gates are programmable and interconnects are programmable. So you can program the gates and interconnects according to your requirement. You can configure some algorithm into the logic gates. So we've just seen the subunits in a system on a chip, the IPs, how it is embedded into VLSI chip, and the embedded FPGA cores. Okay. Next, we come to the design processes and the design metrics for an embedded system design. Okay. Now, when we start with the design, the first thing we do is abstraction. Okay, the abstraction. So what is this? Every problem you will be given with some design problem. Okay, so every problem component, each problem component is first abstracted. For example, display, picture, and text. So if your particular application requires you to design something related to displaying picture and text, the display, picture, and text is created as an abstract class. Then robotic system problem abstraction in terms of controls of motors and different degrees of freedom if you're using certain controlling of motors. Then application software abstracted as concurrently running multiple threads and interrupt service threads. Then you have this different program model that we have seen earlier, that is procedure oriented, object oriented, sequential processes, concurrent processes, and your state machine. So object oriented model may you have class, objects, interface, package. Okay, when you go in for C++. Then you have hardware and software architecture. So this is assumed to consist of multiple layers. Each architectural layer must be well understood before a design. So hardware architecture, software architecture, the layers, you should understand the layers. Okay, I think we can skip some of this. Modular design. Okay, let's come to the design metrics. When we design an embedded system design, there are certain design metrics that we have to keep in mind. These are very important. So what are some of these design metrics? Certain design metrics are your power dissipation, your performance, process deadlines, user interfaces, the size, engineering cost, manufacturing cost, flexibility, the prototype development time, the time to market system, user safety, maintenance. Now, A design process, you call a design process as a bottom to top design if it builds starting from the components. If you start at the component level, this design process is your bottom to top design. Now, you call a design process a top to down design if it first starts with abstraction of the process, and then after abstraction, the details are created. So, top to down design approach is most favored approach because you are not dealing with the nitty-gritties of the lower levels. Now, these are the activities for software design during the software development process. This is your one life cycle, your development process. The first step in the software development process is to model or analyze the requirements of the system. First, you check for the requirements of the system. Second thing you go in for is your design. Okay. Then here you talk about the data structure, the software architecture, the interface, and algorithms. These all are specified in the second stage. The third stage, once you know about the data structure, the software architecture, interface, and algorithm, you go in for the implementation of the design. Now, after your design is implemented, you go in for testing. That is, you test the internal logic and the external functions. Okay. So, if somewhere your requirements are not met, then you go back, you start the process all over again. So when we go in for the top level to the bottom level in the design process, there are 5 levels of abstraction. Okay. The first thing is the requirements. What is the requirements? When you are being given with a system to design, they'll give you with the requirements. Then the specifications, the architecture, the components, and the system integration. So in the requirements, you should have complete clarity of the required purpose. What is the system meant for? What is the intended purpose of the system? The inputs, the outputs, the functioning, the design metrics, the validation requirements for the final development system specification, and consistency in the requirements. So specifications, you should have clear specification of the customer expectations from the product. If your customer is expecting something else and your end product is something else, okay, the requirements will not be fulfilled. So the specifications are required for hardware, for example, the peripherals, device processor, the memory specifications, etc., the data type, and the processing specifications. Then expected system behavior specification, the constraints of design, the expected life cycle specification of the product, okay, because life cycle, time to market, and so on. The process specification analyzed by making list of inputs on the events list, outputs on the events, processes activated on each event. Then the architecture, what type of architecture you're going in for, whether you're going in for the data flow graph model, the program model, software architecture layers, hardware architecture, interface design, how do you integrate the system. Okay. Skip this. Then your hardware components. Hardware components, that is your processor, ASIP, single purpose processor in the system. What are you going in for? Are you going in for a general purpose processor or a application specific or a single purpose processor? Then your memory requirements, okay, your memory RAM, ROM, internal, external flash, or the secondary memory. Then the peripherals and device internal and external to the system, the ports and buses, the power source or the battery in the system. Where is your power source going to be from? So we had to look at the different design processes, models, design metrics, requirements, specifications, architecture, components, and system integration. Next, next we have a look at the challenges in embedded system design, optimizing the design metrics and formalism of the system design. Okay. The first thing that we need to optimize is the amount and the type of hardware needed. So here you optimize the microprocessor, ASIP, and single processor, single purpose processors in the system. That is, if you have selected a particular microprocessor or a microcontroller or a DSP processor, it should be optimized for that particular application. Then optimizing according to the performance, the power dissipation, cost, and other design metrics of the system. Then we optimize the hardware. You try to optimize the hardware, that is your memory, RAM, ROM, internal, external flash or secondary memory in the system, excuse me, and the power source or the battery in the system. So for all this, when we optimize, we take into consideration the different design metrics. For example, power dissipation. We want to keep the power dissipation at a minimum. Then physical size. For example, if you're designing something which is portable, you want the size to be small. Okay? The number of gates, engineering, the prototype development, and the manufacturing cost. The manufacturing cost is high, then you will not have customers for your particular product. Then the prototype development time it takes for the prototype to be developed. If it takes a long time, then maybe some other competitor will come up with a alternate product in the market. Okay, so you'll be at the losing end. So prototype development time, manufacturing costs, these are all design metrics that you have to keep in mind. Then optimizing the participation. How do you optimize the participation? Normally embedded system design, normally we have portable applications. So we can optimize the participation by going in for these different methods, like your clock rate reduction, reduce the clock rate, operating voltage reduction, wait, stop, and cache disable instructions by clever real-time programming, that is using of wait and stop instruction and disabling or controlling certain units when not needed. This is another method of saving your power during program execution. Then disable use of certain structural units of the processor to reduce power dissipation. When certain structural units are not being used, okay, you disable those units so that you reduce the power dissipation. Then process deadlines. So this is again a challenge when we design an embedded system, that is meeting the deadline of all the processes in the system while keeping the memory, the power dissipation, the processor clock rate at the cost at the minimum is a challenge. Then flexibility and upgradability. When you're designing a product, the ability to offer different versions of the product for different requirements. Okay, for marketing and offering the product in advanced version later on, the upgradability. Okay, that is also a challenge. Then reliability. Designing reliable product by appropriate design and thorough testing. Your product should be properly tested, verified, and validated. So this is again validation, verification, testing is again a challenge. Testing, we perform the testing to find errors and to validate that the implemented software is as per the specifications and requirements to get the reliable product. Then verification, this refers to the activity to ensure that the specific functions are correctly implemented. Validation refers to an activity to ensure that the system that has been created is as per the requirements agreed upon at the analysis phase and to ensure its quality. Okay, then we can skip this. Okay, the formalism of steps. First, the requirements and specifications of the hardware and software. This has to be addressed first. Then you define the architectures of the hardware and software, what type of hardware architecture, what type of software architecture you require. Then coding and implementation as per the architecture. Then testing, validation, and verification. Once you have developed your product, the final thing is to test, validate, and verify your system. Okay. Okay. Then we come to the last part. That is, I'm going to take up an example of a design process. Take up just one example, that is your automatic chocolate vending machine. Okay, example of an embedded system. So this is a diagrammatic representation of an automatic chocolate vending machine. Okay, these are the various blocks, modules. You need a keypad for the user interface, a mechanical coin sorter, LCD display or touch screen for the user, a microcontroller based hardware, real-time operating system, software, USB wireless modem, chocolate and refunded coins collector. Okay, this is meant for the customer. So here you have a coin insertion slot. So when the customer wants a chocolate, he inserts a coin. So you need a slot for coin insertion. A keypad on top of the machine. Then LCD display unit on top of the machine. LCD display where you can see the display. It displays the menus, the text entered into the automatic chocolate vending machine, the pictograms, welcome, thank you, and other messages, graphic interactions with the machine, and it displays your time and date. Then you have a delivery slot so that the child can collect the chocolate and coins if refunded. Then interconnection port so that the owner can know the status of the vending machine sales from remote. Your owner will be monitoring from a remote place. So you need an internet connection. Now the hardware units that are required, you need a microcontroller or an ASIC. Then you need a RAM for storing the temporary variables in stack. You need a ROM for application codes and real-time operating system codes for scheduling the task, okay, your different task. Coin is entered, then it will give you chocolate, then depending it will calculate the amount that is to be refunded, the amount will be refunded. So then you have a flash memory for storing the user preferences, contact data, user addresses, user date of birth, identification codes, answers of frequently asked questions, and so on. Then you have an interrupt and timer and interrupt controller, a TCP/IP port for remote control and for getting the status reports by the owner. Then you have this vending machine specific hardware, power supply. Then the software components, keypad input read. When you're typing in the keypad, those inputs should be read. The display, your graphical display, read coins, delivering your chocolate. The software will control this part. This TCP/IP stack processing, TCP/IP stack communication. Okay, so this is an example of a automatic chocolate vending machine. So these are the different hardwares and software that are being used. Okay, I think I have other examples, but I think we can wind up here. If you have any doubts or any questions, can I proceed? Okay, so that is all about embedded system design aspects. I've given you a brief introduction to embedded system design, different types of processors, different types of then the software that you use. Okay, then certain examples and what are the different design metrics that you have to keep in mind, the challenges that you have to keep in mind when you design a specific product. Okay, so that is all. If you have any questions, any doubts, clarifications, I'm open.
Talk about abstraction processes.
Hmm.
We have two types of abstraction. One is top to bottom abstraction process, and one is bottom to top. What are the challenges that are being faced from the bottom to top? Because usually we say like these are very trivial things that we were using bottom to top, and these are very simple in implementing bottom to top abstraction process. What are the challenges actually that we are switching from top to bottom?
Okay. Top to bottom, when you go from bottom to top, from bottom to top, if your design is very complex, very big, complex design, then if you start from the bottom, it becomes very complex because you have to know each and everything. Okay, for example, I'm designing a digital system. Okay, in this case, इसमें everything. If you're starting from the bottom, you have to know the interconnections, circuitry, सब कुछ आपको पता होना चाहिए. But if you're starting from the bottom, then we just divide it into these modules. ये modules है. Okay, I'm just talking about the behavior. We just know about the behavior of that particular product. Then these different modules can be developed by different persons. Okay, so a keypad for the user interface can be developed by somebody else. Mechanical coin sorter can be developed by something else. Okay, we don't start from the bottom. अगर bottom से शुरू करें, then complete. So if your system is very complex, we normally don't go in for the bottom to top. We start from the bottom where we just know about the behavior, the different modules, the functionalities only. Okay, then you have your different softwares which will work on these different modules, and it will create the bottom level. Okay.
So we start from the application level.
From the application level.
Good morning, ma'am.
Morning.
Yeah, I'm from BCD Sirsa. This is Manish Mehta. So, this is the diagram for the ACEM machine.
Okay.
Can you correlate this diagram with the actual coding or actual hardware? Do you have any uh, representation or do you have any material so that we can actually understand about this diagram with the actual hardware?
Okay, I'm just talking about the different design aspects. I'm touching on the different aspects of embedded system design, and this is just an example. I don't have the actual hardware circuitry. I think you can go in for this when you go in for the later sessions. Later sessions, where you can take up a case example.
Okay, okay.
Now I'm just briefly touching upon the various aspects of embedded system design. इसका entire layout I don't have right now.
Because if the application is there, only then we can better understand. I think so.
Yeah, that is there, but then this is just an introductory lecture.
Right, right.
Okay.
Ma'am, I'm Venu from PPS IT, ma'am.
Okay, good morning.
Good morning, ma'am. Can you make me a bit clearer about multitasking and multiprocessing, ma'am? With an
Multi
example possible.
Multitasking, again, that is very in-depth. That is again an entire different topics, multitasking and multiprocessing.
Just with a
It's all
small.
concerned with the real-time operating system. So real-time operating system is again an entire session. So I'll need another one or two session for real-time operating system. But however, briefly, embedded system design, you have a number of tasks and processes that are occurring simultaneously. Okay. So the real-time operating system is manages the switching from one task to another, how to meet the deadlines of a one task, then switch on to other task, and so on. Scheduling and context switching of this task. Okay, these are being carried out by your real-time operating system. So again, real-time operating system, this is again an entire, I'll require an entire session for this.
And multiprocessing, ma'am, how does it differ?
Multiprocessing.
Yes.
Multitasking is when you have a number of tasks. Multiprocessing is again different processing. Suppose you're processing an image or you're processing a speech. Okay, you're processing speech. So different processes going on simultaneously.
Okay.
Okay.
Any interrelation between both multitasking and multiprocessing, ma'am?
Yes, it can be there. Your processes, again, inside your process, when you're running a process, maybe that process it has a different task associated with a particular process.
Thank you, ma'am.
Yes, please, other institutes, if you have any query, please go ahead. Yes, any other query from any other nodal center which is connected? Query from our participants? Yes. You have any query? Okay. So again, we will meet at 2 p.m. and in that session we have Android platform discussion which is required for the designing of embedded systems. So we will be here at 2 p.m. sharply. Thank you.
पता नहीं भाई लंची कैसे तो लग रहा है।
भाई मेल खोल दो मेरी।
भाई खुले जब तो खोलूं, दिख रहा है ये? इधर तो चल रहा है, इधर नहीं चल रहा।
ये ड्रामा चल रहा है, आप इसको देखो ऐसा।
बिना पास के ही चल रहा है।
या मूवी चल रही है ड्रामा तो
Yes.
क्या होगा?
अच्छा देखा, बिना प्रॉक्सी के ही चल रहा है, प्रॉक्सी बिना में मर जाएगा। टिंग टोंग टिंग टोंग।
चलो चलो।
हाँ दिला देते हैं, किसी को बैठा देते हैं परमानेंट यहीं पे। भाग कहाँ रहा है? इना चल बे ओ काका,
एंट्री करवाने इसकी।
एंट्री करवाओ, बैठा इसको यहाँ पे। क्यों क्या होता है मतलब, पढ़ो बैठ के हैं, यही है। निकाल
सेंटर से निकालता हूँ, इसमें लौंडे हैं जैपनी। ठीक है, एंट्री करवा दोगे इसकी?
हाँ कराओ कराओ, उसको सर्टिफिकेट दिलाओ भाई। इना चलो चलो।
इसको रेड्डी को मैं अटकाऊंगा आज तक का। मतलब सारी दुनिया कैप्स में कर रही, स्मॉल कर में करके देखना ही नहीं है दाएं बाएं क्या हो रहा है क्या नहीं हो रहा है।
चलो भरो
सर इसकी वो टेस्ट कर लो साउंड।
So very good afternoon to all. We have our next speaker with us, Mr. Suprit Singh. He is working as assistant professor in the Department of ECE at Baba Banda Singh Bahadur Engineering College, Punjab. He has more than 15 years of teaching experience. His areas of interest are wireless communication, embedded programming, intelligent cognitive wireless systems, and embedded systems. He has more than 20 publications in national and international conferences, as well as an international refereed journal. Currently, he is doing his research work in the field of 5G wireless systems and embedded systems. So today he will give us about the introduction about Android platform and the use of this Android in the development of embedded systems. So I welcome you, sir, in this session.
Thank you, ma'am. So today I'm going to give you a brief introduction about Android systems that are used in embedded systems. Right. So Android platform, embedded systems, because we are quite familiar with the Android. You use the so you are all familiar with the Android system. You all use smartphones nowadays. So, but how it was developed, what are its architecture and underlying principle of operation, right? Main technical, how it's going to operate. So that I'm going to tell you. So Android system in embedded systems, Android platform in embedded systems. So first of all, I'll just give the introduction about an embedded system, right? So I'll just revise out what's an embedded system. So that's the embedded system is that is standalone. It's a chip that includes all CPU is right that's connected to sensors, actuators, which are all operating real time, but they are programmed once or they may be reprogrammable, right? So embedded systems means the system embedded in a chip, right? So system that is embedded into one microcomputer, very small chips, right? Now you operate on mobile phones. So a lot of system that is integrated into very small chips, right? So we have microcomputer, PCs, printers, disk drives. These are not embedded systems, right? So like a system that is programmed for particular purpose, that is embedded system, right? For particular like ATM machine, right? Like the systems nowadays in intelligent cars, those are embedded systems. So let's have a small introduction. Now, definition of embedded systems. There's a combination of hardware and software which together forms a component of larger machine. That's embedded system, right? So no, we have larger machine. It can be any system, mobile system, missile system. It can be anything. So underlying the system, the working is by hardware, right? So the intelligence is being performed by software. So example is like microprocessor that controls an automobile engine, embedded system that is designed to run its own without human intervention, that are intelligent systems. So they may be required to respond to events in real time, right? So all these are the embedded systems. So application areas in our daily life. So can we guess any application areas that we use in our daily life? Washing machines, mobile phones, washing machines, cars, right? Then microwave ovens, right? So nowadays, almost all the applications in all the products we are using embedded systems. So the typical applications include TV remote control nowadays. So there are stereo phones, refrigerators, microwaves, washing machines. So the lot of the systems, alarm clocks, right? So we have electronic toys, very small toys, PDAs, electronic musical instruments, all they have embedded systems. Even a small toy which a child play. So there's a lot of system embedded into this, right? So these are typical areas, and not only this, the list is unending because automation is involved nowadays in everything. So we have medical systems, patient monitoring systems, ingestion systems, sorry, so office equipments, they are all embedded systems like tools, multimeter, oscilloscope, which are being used in labs, they're also embedded systems, ATM machines. Then for transportation we have planes, trains, boats, radars, traffic lights. Nowadays all the system that is being automated and digitally operated, right? So there's a microprocessor involved. Sorry, so these are all the application areas: automobile, engine management, trip computer, cruise control, car alarms, so building systems, elevators, heaters, air conditioning systems. Then we have in agriculture, in space. So everywhere, whatever, wherever there's a automation involved, there's embedded system. Right? Embedded means the system that is embedded. Right now, we can understand this as a like our biological system. Person has, we have a hardware, but the intelligence is embedded into the brain. Right? That's embedded inside. So just by seeing, we can't see, we can't tell what is the intelligence. Right? So similarly, hardware is very small part, and the system which is embedded into that hardware, that is embedded system, kind of software, reprogrammable or whatever we say. Okay, let us take the example of automobile. How many embedded systems are there in modern car, or how many you expect? We have trip computer, electronic ignition, airbags are there, keyless entries are there, ABS or so on. All the systems are automated with the sensors. So how many systems, how many sensors do you expect in a modern car? There, right? So like this, it has more than 85 sensors of 40 different types, right? So different sensors working different for different purpose, and right. So there's again embedded system, example of embedded system. So now let's come to Android platform. Now Android was developed by Google, we all know. It was developed for mobile devices which operate on wireless systems. Right. So Android is a software stack. It's not actual operating system. It's a software stack for mobile devices that includes an operating system, a middleware, and key applications. So we'll just see throughout my talk. I'll be discussing the basic architecture of Android system. What are tools required if I operate, if I want to have my own system based on Android, I want to have my own mobile phone system in the lab, right? Because nowadays it is very easy, right? ARM kits are available in the labs readily, so we can make that it's very easy. So just interfacing, because Android is open software, right? It's not licensed like iPhone, iOS, or any other Windows. Also, all licensing requirements are there. So Android is freeware. It's a free platform, open source. If you know the programming, so you can customize it according to your own requirements. So it's a software stack for mobile devices that includes operating system, middleware, and key applications. So these key applications are customized, right? These are based on based on the application, right? Based on the interface, hardware interface that we are using. So just brief history of this. So we have in 2005 Google acquired Android Inclusive to start Android platform. Then it was a work on DVM, Dalvik Virtual Machine. So all Android system that uses DVM, Dalvik Virtual Machines, parallel to JVM. You might have seen or used JVM, that is Java Virtual Machine. In all the games, whenever we install games or whenever we play games on a PC, so we have JVM, Java Virtual Machine, right? Through that. So on parallel lines, there's a DVM, Dalvik Virtual Machines. In 2007, there was a handset alliance. So there was a SDK, that's a software development toolkit for the Android. So there is a first Android available in 2008, that is version 1. We'll also see what are different versions nowadays, up to now, how much versions have been released and what were the add-ons in each version. So this is a first mobile phone. At that time only iOS by Apple was available, and this was the second system by Google which supported the smartphone. In 2K9, then it was SDK 1.5, there was next version, 1.6 next version, then another, that is in 2K10 there was SDK 2.0. So then, and more releases were there in the subsequent years, and that we'll see as we proceed. Now Android system is an open source operating system created by Google specifically for use on mobile devices like cell phones or tablets. Now it is based on Linux. So we all have Linux, right? Nowadays Linux is a open source. I'm just discussing tidbits of Linux. Right. So Linux operating system is an open source operating system, right? So which is all derived on C and C++. Linux kernel, that's all derived in C and C++. It was started only as a project. So this Linux was started as a final year BTech project by some engineering students, and they derived few libraries and again add on. So we had a full system, a standalone system, Linux operating system at one stage. So there's all open source and derived in C, C++. Nowadays we have different versions like Ubuntu, Fedora, and so on. There are many versions, Red Hat, Linux. Now this is the base of Android. Right. So Linux kernel is used in Android system to interface hardware and upper layers. So to interface hardware with the upper layers, to communicate hardware with the upper layers of network devices, we have Linux kernel as a base for the Android system. Right. So this is readily available, freeware. We can freely download on the internet, and Android system is also we can freely download on the internet and make a new application. Right. So now this is a Linux based, can be programmed in C, C++, but most we have two types of interfaces in Linux. So we have a C, C++ and Java. So both languages can be used to develop an application in Android as well as in Linux. So Android is based on Linux kernel OS, so which is used for hardware. Now you know what is kernel? Kernel क्या होता है? So kernel is actually the basic libraries, like we can say our hex file. Hex file is a type of kernel because it directly interfaces with the hardware. It tells the hardware what to do, right? So it tells the hardware what to do, right? So like a hex file, right? So the underlying program that we say it's a kernel, right? So a group of programs So specified for a particular system to operate particular system in the different environment. So that's a kernel. We have Linux kernel. So it can be programmed in C, C++, but most of the apps they are developed in Java. So then we have Java to C interface that was developed. So which needed the support of Bluetooth, Wi-Fi, 3G, 4G networking, all that is available. Right. So that's done in Android system. So it's an open source operating system. So what we have learned right now is Android is an open source operating system created by Google specifically for use on mobile phones, on network devices, cell phones or tablets. So it's a Linux based kernel. It can be programmed in C, C++, but most applications development is done in Java. Then sports, Bluetooth, Wi-Fi, 3G, 4G, networking, right, and so on. Many applications nowadays are based on Android system. So just before the previous slide, we talked about Open Handset Alliance that was made by Google to the Android version. So to compete with Apple's iOS, so we had an alliance of 47 companies to develop open standards for mobile phones. So there were semiconductor companies, there were mobile operators, there were software companies, there were handset manufacturers, so commercialization companies. So all they made an alliance to develop Android system in 2K7. So nowadays we have STCs, whatever mobile phone, you name it, that operates an Android system. So these are mobile phones, some of the mobile phones that were developed in the first version. First version was in 2K7 or 2K8. Right. So a lot before these were developed on version 1, on version 2. So Sony Ericsson developed its own. Then Velocity Micro. So the devices I'm showing to you, they were version 1. They were operated on version 1 Android. So may not be available nowadays. So let us see the differences, some of the differences between Android and iPhone. iPhone operating system is iOS, that is proprietary. Android system is open source. That's not, we say it's an operating system because it interface the hardware and software, but in actual sense it's not an interface. Right. So OS it's a proprietary. OS is an open source in case of Android. So OS, iOS by iPhone, by Apple, it runs on iPhone and iPod touches only, but OS can be licensed for any mobile phone device. The apps are written basically in C or Objective-C language in iPhone, whereas apps are written in Java language in Android system. So development tools are available. They are available in Mac OS only, whereas development tools are available in many OS in case of Android. Then we have Apple that must approve all the applications to upload on the application store, whereas for Android no approval is required for apps to upload on the Android market. This Android market was the name of Google Play Store when it was firstly developed. Right. So in after 2010, Android market was renamed as Google Play Store when it acquired most of the companies in the alliance. Now in Apple OS, in iOS, some applications are more important than others. That is, some priority is given, whereas in Android case, all apps are considered equal. That is, we choose our own browser. We can choose my own application, any application. So they are all equal. So these are key differences between iOS used in iPhones by Apple and Android. So the internal differences, apps are written in iPhone they are in C language, whereas apps are written in Java in Android case. So again, I'm coming to the basic of the Android. So it's a software stack for mobile devices that includes an operating system, middleware, and key applications. So it provides, it uses the Linux to provide the core system services like security, memory management, process management, power management, and few of the hardware devices. So most of the services, these services are being used by the Android, which are inherited from the Linux kernel. So let us discuss the underlying architecture. So this was just a basic that how it operates. It's just a software stack. We say it's a operating system. In actual sense, it's a software stack, right? So there is a part of operating system, middleware, and key applications, right? So before developing any application for embedded systems, we must know the hardware first. So let us see first the basic how any system we need to program. How it works on the hardware. It can be a microprocessor, it can be a microcontroller, any hardware. Right. So nowadays ARM kits are readily available in the lab, so we can choose those hardware. That hardware, hardware has to be interfaced because hardware understands only machine language. So machine language is in the form of 1010. So around this, the core libraries are developed. That is called as kernel. Any command we want to give to the hardware, will be given to the kernel. So it just translates. It's like you can say it's like kernel is like a assembler. So what it does is it just converts the language or the command to the hardware machine language in the form of 0 and 0 to operate. Then after this there is a shell part. Shell is actually a translator. And at the upper there are apps or programming part. So shell is just a translator which translates the different types of commands given as understood by the kernel. And kernel is actually giving commands to the hardware which operates or performs a particular function. For example, the certain signals are coming from the sensors and how to operate with that signal. So signal का क्या करना है? उस signal को कैसे process करना है? Like the signals are coming from, let us say, an example of our automobile system. Signals are coming from the car, so from the parking system. So how to process those systems and how to behave. So that is, signals are coming to the hardware. So how to operate, how to translate as being understood by human. So that is a part of kernel and shell. Right. So now let us see from this. Let us see the architecture of Android system. So now the basic architecture we have. So basic, there are 5 layers. So we have at the top there's our applications, there are different applications. So we have home, contacts, phone, browser, and so on. There are many applications. So it may compose of many applications. So then there's application framework like activity manager, Windows manager, resource manager, right? Which application is taking, there's a resource manager, then how much hardware requirements are there. Android system is a 5-layer system. Application part, then application framework, libraries, Android run, and Linux kernel. So there are 5 parts. We have, again I am repeating, application. At the application part, we have many applications. An application framework, there is activity manager, window manager, viewing system, package manager, telephony manager, resource manager. So we are going to discuss this all these layers one by one in detail. Another, there's a libraries. In libraries, there's a SGL, SSL libraries are there, WebKit is there, right? Media framework is there, Surface Manager is there. So there are different libraries. Then there's a Android runtime. There's a core libraries along with a DVM. There's a Dalvik virtual machine. I just told you before. We will discuss this in our upcoming slides in detail. What is DVM that I'm going to discuss. Then at the last, there's a Linux kernel. So Linux kernel is actually the system which interacts with the hardware. So we have here display driver, camera driver, flash memory driver, audio drivers, Wi-Fi driver, and so on, power management. So all this is in the Linux kernel. Now let us discuss all these layers one by one. Before discussing, application part is now just there's a we have 2 types of tools, right? One is to develop the applications, another is to develop the platform itself. So the whole architecture that is divided into 2 parts. One is application part and platform part. Right. So starting from the top application. So here we can see it's not a type of operating system. Android is not clearly an operating system. It has few characteristics of OS, but in real sense it's not. It's only a software stack. So different softwares, different libraries are working and they are passing messages to each other. So we have here Android software stack. Let us discuss one by one. We have application layer. So we have home, contacts, phone, browsers, the core applications. So Android provides a set of core applications: email client, SMS programs, calendar, maps, browser, contacts. Now all by parts they have been developed by Google. They are not freeware. Android system is open source and freeware, but these applications are not freeware. Now if I want to develop my own system, I can download Android system. I can install Android system on my ARM processor in the lab, but these applications may not be provided. No application is provided. Right? It's a core system which is freeware. But if I want to use these applications, customize these applications, I need to take permission. I need to take license from the Google. Right? So therefore, only the core system is freeware, but applications are not freeware. Right? So though when we purchase a device, so that company has already an agreement with the Google to install those applications, Google applications. So that's why it's providing us navigation, GPS, or so on, many different applications on a system, right? Because it has already an agreement. Right? Otherwise, because Android is freeware, anybody can use. Anybody having a knowledge of installing Android, I'll just explain tidbits of the installation, how Android can be installed in a lab and how it works. So before that, I just need to go through the architecture, the underlying architecture. So Android system, it provides a set of core applications: email client, calendar, maps, browser, and so on. There are many applications. All they are written in Java language. So this was the application part. So let's come to next layer. There's a application framework. So we have here activity manager, window manager. Now applications provide the interface to the user, but application framework, it provides the activity information of the user to the OS, to the down layers. So what are the activities we are performing? right? So whatever the commands we are going to our smartphone, the commands we are giving to our embedded system. So the application is only processing. That's only passing the commands, but actual the work is being passed to the application framework. That's the underlying framework of the Google. So we have activity manager, Windows manager, content providers, system, package manager, telephony manager, resource manager, so notification manager. So there are different parts which have been developed in a C++ and Java language combined. So a few parts have been developed in C++ and few parts they are in a Java. So it just enables and simplifying the reuse of components. Developers have full access to the same frameworks, APIs, application programming interfaces used by core applications, and users are also allowed to replace the components. So we have updations. The notifications come from notification manager, right? So the location part, GPS system, that is handled by the location manager. So there are separate parts in the application framework. So telephony manager, then we have resource manager. So different resources, they have to be optimized, right? So what are the memory being used by the different programs, the resources, the CPU power or memory management, all that is done. Actual sense it is not done. It is the memory management information is passed to the down layers, right? So this application framework only tells that which application requires how much memory. So the second layer, there's a application framework. Next is now the main features. Let us see about the application framework. So we have view system that is used to build an application, including lists, grids, text boxes, buttons. So whatever web browser, whatever information is there, what we are seeing on our mobile phone, so that is a part of application, right? So that is handled in the application framework by view system. How the application will be viewed by the user. Another is content provider. So it enables the applications to access data from other applications or to share their own data. Right? So what we have is content provider. What it does is it just picks up the different types of contents from where to fetch the contents, like from the internet, where from the internet, right? Particular locations, different locations. There's a list, full list. This content is being accessed from this. These contents are being required by this. So there's a full list in the content provider, right, inside. Then we have resource manager. So again, in the resource manager, it provides access to known code resources, strings, internal graphics being used, right? So now we can customize this. So we can customize this resource manager as per requirement. Even different companies nowadays, they just take out the Android, they download the Android system, open source is there. So they download this from the internet, from the Google website, from the Google. Then what they do is they just have their own resource manager, right? Nowadays, how the different companies, new companies, in very short time, they are floating their different products very fast. How? What they have is nothing. Just they have ARM processors, ARM 9 or whatever, right? Different processors readily available in a discrete form. They do nothing. Just interfacing. Interface this RAM, interface this ROM, right? Then what else? LCD is available in the market, right? Touch is available in the market. Just interface, and they just do their resource management. They just customize as per their own. They make their own logo and make few applications and just float that product in the market. Nothing else, right? So even you will see in most of different companies' products, there's only difference in the resources. This having different processor, another company having different RAM, different ROM, only this, nothing much. Or a different category in the, you can say, in they just do optimization, right? Optimization of resources, right? Again by the resource manager, customize the resource manager. So providing access to known code resources, localized strings. I'm just reading graphics and layout files. Next is we have notification manager. Now this notification manager enables all the applications to display customer alerts in the status bar. So what to do, how to do, what activity is required, so in which state our system is operating. So I'm not talking about only our mobile phone because whenever we talk about Android, our mind is there. I'm talking about any general product. Nowadays, specifically in India, we have only Android based mobile phones. But when you can see the internet, Android based washing machines are already there. Android based microwave ovens are already there in the market, right? So Android based home automation systems are already there, right? So being although they are not popular in India, but they are already in the market, right? So notification manager is there, enabling all applications to display customer alerts in their status bar. Activity manager, it manages the life cycle of applications and providing a common navigation backstack. Right. So what are the activities they are being performed? So activities, what are the different activities the user is performing? So that is all handled by activity manager. Similar in the Windows also. So whenever we click at any item, that is being recorded as a log in the window. Right. We click, even a single click is recorded, single activity is recorded in the window, in Windows operating system, because we are all familiar with the Windows operating system in our PCs. We normally operate. So what we have is so normally all the clicks. Now there is also notification manager in Windows. Now let us see how it works in the Windows. This notification manager, resource manager, that is the idea is being taken from the Windows, right? So let us see how it works. Whenever I click, you must have seen. Whenever I click a particular item on the Windows, right? So there's a time I just click and response from the hardware, actual hardware. So whenever I perform any activity, I'm just talking about our normal PCs. Whenever I perform any click or any activity in the normal, what happens? There's a time frame that it has to, the hardware and OS has to pass the information to the hardware, and the hardware has to respond to my click. Right? There's a you can say timer starts. You might have noticed many times we have the system is not responding, wait or continue, right? Because how it comes? Because there's a timer, internal timer starts with every click. Right? So similarly here, so we have notification, resource manager, and of the similar kind. Whenever we press any key, whenever we press, we perform any activity, so there is a notification by the shell to the kernel and correspondingly to the hardware, internal hardware. The command is sent. Right. So depending upon it checks all the system. Then depending on different resources available, different resources being used by different applications, so it allocates the resources to the particular applications. Right. So this we have. This all is done in application framework in Android. So let's move next in the next stack. So again, down the stack we have libraries. So we have Surface Manager, then Media Framework, SGL, SSL libraries are there. So these libraries are performed. These libraries, they just perform the work of translator. They get the input from the application framework and they just translate the different activities and give the output to the Linux kernel. Or okay, so they just pass on the information to the Linux kernel. So as well as they also pass on the information to the upper layers. So there's a both way. So it's a both way. So it passes the information to the upper layers as well as it passes the information to the lower layers. So we have it including a set of C++ libraries used by components of Android system. So these libraries are again freeware. They have been developed in C++. They can be developed in C++ or in Java. Right. So exposed to developers through Android application framework. So application framework, it just interfaces the application to the libraries. So next is Android runtime. So I'll discuss this in much more detail. Android runtime consists of two parts: core libraries and Dalvik virtual machine. That is DVM. That was a system that I was talking about before. That is DVM. In the definition we just saw, is based on DVM, Dalvik virtual machine. So core libraries and DVM. So it's corresponding to JVM, that is Java virtual machine, that we install during any if I want to play in games, we have JVMs, Java virtual machine, runtime Java, to be installed on PCs. So these core libraries provide the functionality for the Java language, like data structures, which type of data structures, linkages are to be used, utilities, network access, graphics. So the core libraries providing most of the functionality available in core libraries of the Java language. Then we have APIs, data structures, utilities, file access, network access, graphics, etc. So all this is a part of core libraries. Now this DVM, there's a Dalvik virtual machine. It provides an environment on which every Android application runs. So it provides an environment. Like for example, our Windows, it provides a desktop environment on which our any or every application opens. Similar to that, DVM provides an environment to every application. That we say now in Windows OS, we say there's a desktop. In Android, in technical language, that we say is DVM, Dalvik virtual machine. So each Android application runs its own process with its own instance of DVM, that is Dalvik virtual machine. So this DVM is written in such a way that device can run multiple virtual machines efficiently. Right? Now whenever we click on any application, whenever different applications run, multi-user or multi you can say threading, right? So each process is given a particular ID. So there's the work of DVM. Whatever different resources they are to be given, what are the different resources that are to be used by the different applications. So that's why provided by DVM in the Android. So providing environment on which every Android application runs, each Android environment on which every Android providing environment on which every Android application runs. Each Android application runs its own process with its own instance of DVM. So it's a register based virtual machine, DVM. Now here in DVM, the files or libraries which are written, so they have extension as .dex. In Java, we had extension of .java, and when the Java was made object oriented or different libraries are written in Java, so it is converted to .class. So whatever we write in Java, whatever programs we write in Java, so the extension is .class. And what we have when we transfer that, when we translate that in Android, so in DVM we have .dex. So now let us have a look on DVM. Dalvik virtual machine executes the Dalvik executables, that is .dx files format. So now this format is optimized for minimal memory footprint and compilation, because we have very limited resources in our small system. In an embedded system, we have limited resources as compared to our general purpose PC or general purpose systems, right? So embedded systems, mostly it composed of microcontrollers which are particularly designed to perform particular function. So we have a here .java that is translated into .class, which is in turn translated into .dex. That's a Dalvik executable file format. So now this all DVM, unlike JVM, this all depends upon Linux kernel. Right? It's a part of Linux OS for threading, for low level memory management. That all depends on Linux kernel, because Linux was already available freeware in different forms in Ubuntu, Fedora, or so on, right? Red Hat Linux, Mandrake Linux. So Linux was readily available. That's also freeware. So here, all instead of redesigning from scratch, the Google team, the developer team, they just reused all this Linux kernel and they just customized it, worked on that, optimized all the kernel to operate on limited resources, limited hardware resources. Whether it is a, you can say, processor in terms of memory, in terms of, you can say, display, in terms of input, in terms of output. So this all has been customized to operate on limited resources. So Dalvik VM, let us summarize. So Android runtime consists of Dalvik virtual machine, is a subset of Java developed by Google, optimized for mobile devices, for battery, for better memory management, for optimized battery utilization, and so on. There may be many optimizations that have been done during customization. So it runs .dx files that are compiled from .class files, and also introduces some new libraries. So DVM does not support some of the Java libraries. So because it is customized into new. So it's previously as a Java virtual machine. It has been converted into DVM, Dalvik virtual machine, but it doesn't support some of the libraries that are available in Java. So the difference between JVM and DVM in Java virtual machine and Android's Dalvik virtual machine, the basic difference is the applications are boxed, right? So because that means the application can only access its own data, or otherwise we need to set the permissions that how much data it can access from other applications or from the shared pool, right? So by default, each app is run in its own Linux process. The process started when app's code needs to be executed. Whenever we perform any activity, the code starts. So how to respond? Then it goes to the down layers, from application layer to the application framework. So how much memory to be allocated to a particular resource? That's the work of Linux kernel and runtime libraries, which keep the you can say the pool of used and unused resources, the list of how much memory is being used by which resource, which program. So all that in detail. There's a list internal. There's a resource manager in application framework we just saw in the previous slide. Then each app runs its own Linux process. Threads can be started to handle time consuming operations. Time consuming means like processing part, like for example to handle the information from the different sensors, right? Now in normal airplane, there are more than 300 sensors are there at different parts, right? So at the same time, the input is or signal is coming from all the sensors, right? So just by sampling at different times in microseconds, all the sensors have the signals, they have to be handled somewhere, they have to be combined together to form particular decision, right? So that part that is handled, to handle that part there are threads, different threads at the software level, right? So at the runtime, so each process it has its own DVM. By default, each app is assigned a unique ID and permissions are set, so apps files are only visible to that app. It's very important. Now this line is very important. That is, the permissions are set so that apps files are not visible to other part. They're only visible to that part only. So this is a DVM, Dalek virtual machine. So let's come to the kernel part, Linux kernel. So in this Linux kernel, we have display drivers, we have camera drivers, keypad drivers, Wi-Fi or some. What are the different sources available? Now, first of all, what is a driver? Driver is again a program which takes the input in normal language. Driver is a program which takes the input from a system and gives us the desired output. Like camera, it just clicks on, so all pick, then saves to the memory. So what's the resolution? What's the clarity? There's an internal. There's the image processing part, right? So digital image processing part. Then we have speech processing part available in all the nowadays in all the Android applications. So how to handle the actual hardware? Because we are at the user level, the user is seeing the pic, but actual how the signal is being handled by the photosensitive layer of the camera, or how our flash memory is working. Because again, the same thing is applies to all hardware. That is, our whether there's a flash memory in our Windows, in our PCs, or whether that memory is in our mobile phones. So it understands only machine language, 0101 language, right? So in our machine language, so the drivers are there just to make that particular system understand how my user is giving commands, right? So what are different commands my user is giving? So to understand those commands, so and to give it to the actual hardware, these are drivers. So audio drivers, power management, so how much power is being used by which processor? Because nowadays what happens, microprocessor is one part, the graphics processor is another part, the image processing part is different, speech processing part is different. So all the different systems, they have been all the system has been subdivided into subsystems. So the underlying principle is only the signal processing everywhere, right? But the application area is different. How to process the signal, that is different. Right? So we have here Linux kernel. So that is again kernel that is again readily available, openware. So we have so all the Android system that relies on the Linux kernel for core system services like memory management, process management, network stack, driver model, security, and so on. So this is a part actually which provides the abstraction between the hardware and the rest of the software stack. Right. So it provides a abstraction layer between the how my hardware will be working and how my software should respond, or vice versa. How my software is working and how my hardware should respond. Right. So both ways. So these drivers are open source. So we can customize any drivers. We can customize our own, right? So as per our own requirement. For example, to interface 13 megapixel of camera to my ARM processor in the lab, I may be requiring to write a program in ARM processor so that my signal from the camera it is stored in particular memory area, or how my signal is to be processed, and I need to view that signal on the display device, right? So I need to write a program, or to handle the like Wi-Fi drivers, they are readily available, audio drivers. So how to handle the signals coming from different sensors? So I can write my own drivers, right? So Linux kernels drivers are available. They're open source, right? So this is the all underlying architecture of the Android system, right? I'm just revising. Let us summarize. It is 5-layer architecture. On the uppermost part, we have application layer. Then we have application framework layer. There are different libraries. Then we have runtime, Android runtime. Then we have Linux kernel, right? So there's an underlying which actually interacts with the hardware and provides abstraction to the software stack. So there are different versions. So that were developed by the Google. First version came in September 2008. Then next. So actually all they were open source except version 3. All the system was open source, right? And most notable features, or you can say the improvements that were developed. So version 2, there's a exchange port upgraded, just in time compile upgraded in 2.2. Then in 2.3 we had, but up to 2.3 or 3 there was not so much popularity or usage. After it had a USB port in 3 or 3.1 version, it had particular APIs upgraded, that is application programming interface, right? So there was, so after that, so the use of this system that increased many folds. So we had then 4.0 version, 4.1, 4.2, then next we have 5. So again in subsequent years there are many versions available, right? So these are just the code names. There is a Jelly Bean, or these are just the code names given by the Google to the developers team to upgrade particular you can say only particular application areas, or you can say to upgrade the particular interfaces. They are just the code names. So next part I'm going to discuss, that is Android for embedded systems. Now I can develop all the system in my lab, right? Because nowadays in our labs, in particularly in electronics labs, we have ARM platform available, ARM boards available, right? In our graduate or postgraduate, you can say in the syllabus we have ARM programming. So how can we interface? How can I develop my own embedded system based on Android? Not for cell phone, for any application, just you name it. So any application, Android can be used. So there are two main pieces required to get Android working on your embedded system. One is Android compatible Linux kernel. Another is Android platform. So the kernel is basically interface that we have just discussed, that provides an interface between the actual hardware and the software. It only provides abstraction between the actual hardware and upper layers of the software stack. So Android platform is also called AOSP, that is Android Operating System Open Source Platform. Now for Android, minimum display size required is 2.5 inches, right? So below that size it doesn't work, it doesn't support. Its APIs, application programmable interfaces and drivers, that doesn't support below this, right? So this can be, this display size or interface, it can be a both ways. Both ways means a smart display or anything else. Like Smart display means a touch display which has input and output both. Now our touch screen it behaves as an input device as well as output device, right? So we can download Android freeware from the website is given for android.googlesource.com. There's a freely available Android platform we can download, and we can customize that to use on our own embedded system, designed for our own embedded system, right? So what we have is, up to now, we have two main pieces. One is Linux kernel, Android compatible Linux kernel, and second is Android open source platform that is required. Though there are some restrictions. Now restrictions are like Android bot, that is you are just seeing here on the right top corner of the screen. Android robot, there's a green colored robot that is seen everywhere all around the things that have Android. So its role is similar like a Linux penguin. Now this we can't use because that has been proprietary by the Google. We can't use this, or neither we can customize this. We need to take the permission license. Another is Android logo. Now this logo is, again, we need to take permission from the Google to customize it. Now what happens? This is a set of letters that spell out Android that appear during the device and emulator boot up. So nowadays what happens? Whenever we purchase any product based on Android, any product, not only mobile phones, whenever we purchase any product, the logo of the company comes, because this Android logo has been customized. They customize this by taking license or particular permissions from the Google. There's a you can say agreement between the different companies to use the particular set of libraries and to customize that according to their own. So same as this, like Android Google, Android logo, they are not authorized to use that logo under any circumstance. So then, right, then there are few more restrictions that are available on the website, right, from where you can download. This is the website name given, android.googlesource.com, right. So now let us discuss how to develop an Android embedded system based on Android in our labs from the scratch. So developing an Android based embedded systems from scratch in the lab. So we all have ARM processor boards available. It can be ARM7, it can be ARM9. Memory chip, EEPROM, we can have 1 GB or minimum requirement is 256 MB. RAM, again we have 512 MB. The minimum requirement is 128 MB. But when this minimum requirement, what is meant by minimum requirement? Minimum requirement means only the Android will cover up that space, right? So to you can say install or to customize to use the application area, right? So to install particular applications on that system, we need somewhat more memory. So normally, typically, memory chip of 1 GB, RAM of 512 MB. So it covers the basic requirements. Then we should have in a lab a PC on which to install Android emulator v2.2, a PC with Android Studio. There is a software, Android Studio, that is a SDK, software development kit, available to develop any application on Android. So display with minimum 2.5 inches size. Any other auxiliary accessories like camera, different sensors, gyrometer, accelerometer, whatever, that depends upon the application, right? Like for example, for washing machine, I want to have a Android based washing machine, or if I want to have Android based microwave oven. So in that what happens, the different sensors, whatever temperature sensor is required, right, in case of microwave oven, right, so different heating equipment is required, magnetron or so on, whatever microwave generators are there. So we need to handle the signals from those, or to pass the signal, to give the signals, to command those, or to get the signals from the sensors. Right. So there is a basic requirement to develop an Android-based embedded system in a lab. Now ARM7, then emulator, I'm just repeating, Android Studio, touch display or without touch customized display, and a PC. So tools. Now there are two different set of tools for Android development. Those tools for application, one is those tools which are required for application development. Another is those tools for platform development. So there are different kinds of tools available and different kinds of tools required to develop application part, application framework, that part. And if I want to work on platform means our lower layers, that is Linux kernel. Then we have runtime libraries. Then we have core libraries, right? So to work on those, on that part, different tool set is required. To work on, you can say, applications, to work on application framework, different toolkits, different tools is required. So there are two different set of tools. One is those tools which are required for application development and application framework. And is those tools which are required for platform development, right? Like kernel, runtime, and core library set. Then there's an Android emulator that's again freely available on the internet, right? So in the emulator there are different steps to emulate the system, but the basic system, let us see in the next slide. So emulator hardware can be ARM5 CPU, corresponding memory management unit, a 16-bit LCD display, one or more keyboards may be interfaced, a sound chip with input-output capabilities, then flash memory partitions are there, GSM modem or so on. These may be required to emulate my application developed in Android on actual hardware. For example, in lab I have just ARM kit available. With that ARM kit, if I interface, let us say, some memory like 1 GB memory, ROM, some RAM, runtime memory, that's a RAM, then I interface certain, let us say, some display, right? Then GSM modem or different sensors. Now to interface all this, I need to develop my own drivers, or else I can use drivers readily available from the manufacturer, or the drivers that are the part of Linux kernel, right? There are three options. So developing own drivers, or drivers that are come from the manufacturer, or develop the drivers that are, or use those drivers that are the part of Linux kernel. Then what else? Then I'll just connect all those to the PC, having Android emulator, Android Studio. Now Android Studio just develops my application. To run that application, to see the effect, to debug that, I need a runtime environment Android emulator. But there are certain limitations in the emulator. So do you know the difference between a simulator and emulator? So what is a simulation? Simulation क्या होती है? Simulation means operating in virtual environment, creating virtual environment for a particular system. For example, I want to simulate some communication model, some communication system. I just take a random bits, modulate that, transfer on the AWGN channel, or some real-time channels, Nagakami channel, relay channel, right? Then what next? We just design a receiver, for example, in MATLAB, right? So we do simulation. Simulation means we just create virtual environment. and see the effect. Emulator is we see those effects on actual hardware, right? So emulation is done with the help of in many of the applications, in many of the you can say hardware nowadays, boundary scan technology is used, right? So emulation is on hardware. What happens in emulator? On emulator, I can just for example in simulators, when I want to debug my program, हम क्या करते हैं? I just have breakpoints, एक एक लाइन को एग्जीक्यूट करके देखते हैं सेपरेटली, डिबगिंग हो जाता है, पता लग जाता है. सो आई जस्ट कम टू नो दैट कि ये लाइन को ये इनपुट जा रहा है और ये आउटपुट दे रहा है. सो दिस पर्टिकुलर माय कोड, माय प्रोग्रामिंग कोड is getting this much input and giving me this type of output, right? So what we have is in emulator, I actually connect through USB or other interface. There's a nowadays USB has been a standard. Before this, there was a boundary scan technology, that was JTAG standard for debugging or emulation. JTAG is Joint Test Access Group. So what happens in the hardware, in the actual hardware, there is particular JTAG bus is there, right? So I just explain here. Working emulation means working on real hardware, right? So what happens, those hardware, that part of hardware that supports the emulation, ये क्या करता है? Let us say a typical microprocessor or microcontroller. So I have processing unit, I have different resistors available, I have different devices. So these are processing. Now here what we have is pins. Now what happens? Because in software, when we do the emulation, when we do the simulation, what happens? We can just see the different lines, right? Executing one line at a time of the programming code, right? So it's very easy for software developers, but for the as electronics or communication people, it's very difficult what is going on inside our hardware. Hardware के अंदर, because it is working on 1010. So 1010 कहाँ पर फंस गया या कहाँ पर रह गया? So we can't see that, right? So how to see that? There was technology that is called JTAG. The acronym for Joint Test Access Group. So Joint Test Access Group that works on boundary scanning. What happens? There's a particular bus. हम हार्डवेयर के अंदर क्या करते हैं? एक बस डिजाइन की होती है बाय द मैन्युफैक्चरर. So वो क्या करते हैं internally, that is connected to each and every peripheral part, each and every part inside a microprocessor or microcontroller, like internal cache memory, internal RAM, जितनी भी RAM है. So ये अब what I do is there are 4 pins. One is TDI input, TDO output, another is T clock, and third is P mode. So there are 4 pins: input, output, clock, and T mode. Test mode, test clock, test data output, test data input. So हम क्या करते हैं? So we just send the signals from the PC and we can see इस RAM location में मेरा क्या चीज store है. So if this is my sensor, यहाँ पर अगर मेरा कोई sensor लगा, sensor का सिग्नल कितना आ रहा है मेरी RAM में, कितना स्टोर हो रहा है एक्चुअली में, राइट? और ये प्रोसेसिंग कहाँ पे चल रही है, वी कैन जस्ट सी ऑन द पीसी, राइट? सो ऑल दिस वी कैन जस्ट सी थ्रू दीज पिन्स. I just connect these pins to the JTAG driver and then to the USB. And we can just see कि इंटरनल मेरा एक्चुअल हार्डवेयर के अंदर लाइक आई हैव रैम और रोम और माइक्रोप्रोसेसर, मेरा माइक्रोप्रोसेसर एक एक स्टेप में क्या क्या कर रहा है, एक्चुअल हार्डवेयर में कैसे प्रोसेसिंग हो रही है, दैट वी कैन सी, दैट इज द एमुलेशन, राइट. So another part is simulation means in virtual environment, emulation means in real time environment, right. So that's the emulator. Android emulator means I just, when I need a new application, so I need to I just need to emulate that, test in a real time, right, how the customer will experience, how my hardware is responding to that application. So I need to emulate. There's a Android emulator available for those applications. So but there are certain limitations that are here. There's no support for actual placing or receiving phone calls, and there's no support for USB connections, there's no support for camera, video. Just emulators, it provides basic functionality. Like for example, again, some Windows, what we do, क्या करते हैं हम, we operate that Windows in safe mode. तो safe mode में क्या होता है, so only basic functionality test हो जाती है, whether the problem is with the basic functionality or the problem is with the drivers, ये हम देखते हैं. So whether my core window kernel or shell part is corrupt, or whether my display drivers or different, the problems with the drivers, यही हम. So similarly here, so this emulation that only provides that whether my kernel part, core part is functioning as per my optimization or as by my as per my algorithm that has been developed, उसके हिसाब से ये काम कर रहा है कि नहीं कर रहा, right. So it provides those functionalities only, right? So it doesn't provide a support for different devices, doesn't determine connected state, doesn't determine the support for battery charging level or some SD cards, some Bluetooth, but it provides a basic functionality, right. Processing being done by the my ARM processor or whatever different processors nowadays available in the market, whether it's a 32-bit processor or 62-bit processor, whatever, right. So how my RAM, whether my RAM is interfaced properly, whether my ROM is working properly, whether you can say my display is working properly, right. So to see just the basic functionality, we emulate the system. So setup development environment, software development, or you can also say software development environment. So what we have is as steps. Just if I want to develop my own software, install, first step is install Java development kit, Java virtual machine, that provides a Java virtual machine environment, because DVM that we just discussed in your previous slides, there's a Dalvik virtual machine that only, there's an upgradation version of Java virtual machine, and even though that doesn't support the previous functionality, but it requires JVK, Java development kit. Then it installs Eclipse IDE that provides an interface. Then another step is download and unpack Android SDK in the form of Android Studio, I just discussed in your previous slides. Then install Android development tools plugin for Eclipse. Then all different install instructions are available on the website. So all this, these are different steps that are required just to develop. So after development, what we need to do is we need to emulate. So one is a software part, another is a hardware part. So software part means developing application, then application framework. So then on the hardware part becomes complete knowledge of underlying hardware architecture. So to develop a kernel, we need to have complete knowledge of hardware architecture. मेरा जो microprocessor है या microcontroller, कौन सी different you can say hardware, you can say communication ports को support करता है, different there are different nowadays communication, internal communication के लिए different standards हैं like SPI, I2C. I2C is Inter IC Communication Protocol. Right. SPI is Serial Peripheral Interface Protocol that was developed by Philips. Right. So then there is another. There are many different, like they are same like parallel port or serial port that was developed in the previous applications in like 8051. Right. That uses our UART or USART. Right. So similarly, if we go to PIC supports many different interfaces. Like PIC microcontroller, AVR series of microcontrollers. So the embedded systems that are based on AVR, they support many different, you can say, different interfaces. Like we have SPI interface. I just told you I2C interface, USART, UART, and parallel interface PSP. That's a parallel slave port is there, right? Then there is also you can say just change signal interrupt. Like there is change some signal, it will interrupt, right? So there are many different interfaces, internal interfaces available nowadays in the microcontrollers, right? So this is all like setup development environment. So this is a just the layout of producing an Android app. We have Java code for Java, then we convert that into bytecodes having a dot class extension and other class extensions. They are added together to make a Dalvik exe. So again, in Dalvik exe is one part that provides runtime environment. So to provide the user interface, हमारी application दिखेगी कैसे to the user, how it will behave to the application framework in the second layer, right? So the top is application layer, second is application framework layer, just we discussed in the underlying architecture of Android. So वो कैसे behave करेगी, उसके आगे कौन कौन सी libraries access करेगी, so kernel को कैसे command देगी और कैसे how it will communicate with the kernel, it will take the commands from the kernel or it will notify to the user the different states of the hardware. So these are they are combined together. This you can say DEX file for developed by the DVM Dalvik virtual machine. It is combined with the XML and the resource lists, right? So and final there is a .apk application. So we combine this, we just change that into our runtime APKs, right? So that's how our all Android application is developed, right? So we just application. Now next is our application development components that are available. There are 4 components available. First is the activity. So basic component in the application development, there are 4 types. One is activities, services, broadcast receivers, and content providers. So first is an activity. Activity is any response or any, you can say, command given by the user to the underlying hardware or to the down layers, the core layers or other layers. So activity is a functional unit of an application which may be invoked by another activity, or it has a user interface of some form. Application may incorporate a number of activities. One activity may be nominated as a default, which means it may be directly executed by the user. So this is an activity part. This is the first part. Another is a service part. That's a service that is similar to the activity. No, activity comes at the application part that we just whatever we discussed, the 5-layer model of Android application. Activity is based on application part. So उसने activity ने service क्या provide करनी, कैसे provide करनी to my underlying operating system, underlying hardware. There's a service. Service part is concerned with my activity framework. So this service part is with the activity framework. How my application will behave to the framework, right? So what are the commands that are needed? What are different resources required? कितनी मेमोरी चाहिए? उसको सेंसर से अगर सिग्नल आ रहा है, उसको कैसे सिग्नल चाहिए? कैसे मेरा अगर आर्म किट है मेरे पास, सो मेरी आर्म किट को कैसे सिग्नल प्रोसेस करना है? so that it gives to the application part, application layer. So services is a on the second layer. It's a similar to an activity, except it runs in a background without the user interaction. Right? So that is a part of application framework. Example of a service might be a media player that plays music while user performs other tasks. There is one layer of service. There's one part of example of service. Third is broadcast receivers. These are just components. If I want to make my own application, Android-based application for my own embedded system, right? So broadcast receivers, if I want to have my standalone system, Android system, if I want to develop based on Android, or if I want to have network-based, like our mobile phones based on Android. I just told you before that Android is not only used in mobile phones. Like if I talk about mobile phones or tablets, they are network based. If I talk about washing machine, Android based washing machine, right, that is being controlled by my own cell phone. There's not a network based. There's only a that can be a standalone, or that can be interfaced to one commanding system. For example, microwave oven, another application. Like again, Android based microwave oven, they are already available. Not popular in India. They are available in the market. Right, so Android based watches are already nowadays available, right? So whether I need a broadcast, this is the third part now. There's a whether I need broadcast receivers or I don't need that. So it simply responds to the broadcast messages from other applications or from the system on the network or not on the network. For example, it may be useful for application to know when a picture has been taken, right? So it's when activity has been done, at what time activity has been activated by the user, or a service has been performed. So there's all the broadcast. Internal broadcast is also there, external broadcast is also there. So broadcast receivers. And lastly, content provider. If the user needs particular content, उसको कैसे provide करना है, कौन सी वेबसाइट से provide करना है, और internally कैसे provide करना है, so किस memory से data लेना है. So all that is a part of content provider that supplies data, and content provider is a part of kernel that actually interacts with the hardware. Hardware में कहाँ मेरा data store है in ARM, because basically Android works with the ARM 8051 or you can say PIC or AVRs. They are not nowadays. They are not yet supported by Android. ARM 7, ARM 5, ARM 9. That is that hardware is supported by the Android, right? So ARM based, we can develop any embedded system, and we can install Android. So I just told you it's a freeware you can download from the internet. So content provider supplies data from one application to the other on request, and such requests are handled by the methods of content resolver classes, and that are handled, and the data may be stored in a file system or whatever the user requires. So we need to program that कि मेरा data कहाँ पर store होगा, मेरी command कैसे जाएगी, right? All that. So this is the 4 components for the application development that is on Android. And ये application development कहाँ करेंगे हम? On Android Studio. Android Studio it's a software that can be downloaded from the Google. I just told you the website. So what we discussed, I just summarize all the lecture. What we discussed at the very first, we discussed the embedded system, the basics of embedded system. Embedded system कहाँ का apply होता है? Nowadays embedded system is available everywhere in all the applications, in all the daily applications we just discussed. There are many daily applications, not in a single devices that is without embedded system, right? Then we have examples of embedded system we just saw. Then we just saw Android system, the basic definition of Android system. It consists of middleware, OS, and kernel part. Then we just discussed all the architecture in detail, the 5-layer architecture. There's a application framework. Then we discussed core libraries. Then we have runtime, Dalvik virtual machine parallel to the JVM. Then we discussed Linux kernel, where different services which are being provided or which are to be provided by the different layers in the Android. That we discussed in detail, right? Then we discussed the difference between Android platform and iOS, because when the Android was started in 2005, only one operating system was there, right? to support smartphones or to support that functionality, that kind of functionality for which the Android was to be developed. In 2005, there was only iOS by Apple, right? So parallel to that, Android was developed. We just saw the differences. What are the differences? Then after that, how to develop Android based application from scratch in a lab. Lab में हम अपनी, because nowadays in the labs ARM kits are available. They are in the part of syllabus in a BTech or MTech nowadays in most of the universities. So Android, from the Android kit, I can just interface the simple components and I can download the Android Studio JVM from the internet, and I can just customize theirs and run my own application. Just I can interface the different sensors, right? So then the different parts, application development components, there are 4 components we discussed. So that is all from my side based on Android. So how to develop an application on embedded system based on Android, because nowadays Android is being used in every application. This is because it provides a very easy interface with the user, right? So that was all from my side. So next is from next 15 minutes. If there are any questions, any doubts, you can ask. Repeat. Any core applications, for example, what you try to say? No, all applications happen and they are proprietary. So this is a core application, but it's a proprietary. Right. So we need to take the permission, or we need to have an agreement with the Google. Otherwise, as such, no such application works at this time. This Android is a core on the interface. So this is a main actually book that Google has. They have in their. Yes. Right. Applications, in the sense, application means that I want to say that application means interface, right? How to interface with the touch display, how to interface with the actual input-output devices, how to interface with the sensors. That kind of driver, which are provided by the Linux kernel itself. They are part of Linux kernel itself. They are not part of the actual upper layers, which the Android is providing. वो उनका पार्ट नहीं है, so वो कर्नल का पार्ट है, वो प्रोवाइड करता है. As such applications, they are proprietary. जो बेसिक ड्राइवर पार्ट है वो प्रोवाइड करता है Linux, and Linux is also open source, that we have already seen. So any other query or question? Middleware means the middle part. It can be an interpreter, it can be a compiler, it can be an assembler. So actually when I talk about assembler, I am talking about that my assembly language programming is being converted into machine language programming. That is actually assembler. और इंटरप्रेटर क्या करता है और कंपाइलर क्या करता है? कंपाइलर मेरी C++ को हायर लेवल, यू कैन से हायर लेवल लैंग्वेजेस को मेरा डाउन कन्वर्ट करता है. लाइक C++, for example, we have Keel compiler for 8051. We have real view compiler for the ARM system. For the ARM system, we have real view simulator. There's a software, there's a real view, right? So वो provide करता है. So that's a middleware. So middleware is a common name that is given जब हम ऊपर वाला एप्लीकेशन लेयर निकाल देते हैं और नीचे वाला कर्नल पार्ट निकाल देते हैं, जो मिडिल में आता है वो दैट ऑल इज मिडलवेयर. So any other query?
Can we have this Android system without touch screen?
Yes, of course we can have, because touch is nothing. Because most of the people, we are fascinating about touch screen. Touch screen is nothing. What is touch screen? We need to understand. Touch screen is input device embedded on a output device. So in our commercial screens, input device is different and output device is different. So there's not much difference. But how to handle the data on a display, how to get the input, how to give the output on the display, and how to get the input to the system from the display, on that part is different. Baki rest functionality is all same. So that can we can have different display devices different and output devices different, because display is just an output device. We can talk about any LCD or LED signboards nowadays are there. They are all you can say devices, output devices. Input can be anything, mouse based, keyboard based, or any other joystick based, anything. So any other query?
Sir, queries from participants.
Hello.
Do you have any query, please?
Hello. Good evening, ma'am.
Good evening.
We are from PVP SIT.
Yes, ma'am. Please go ahead with your query.
Yeah. What is meant by SDK 86, ma'am? SDK 86.
Yes. SDK 86 is software development kit for 86. 86 is actually 32-bit को हम 86 बोलते हैं, और इसमें करना क्या होता है, वो x86 means that was name jointly given to the like 8086 based processors. It comes in 8086, 186, 286, and so on to 486. I just remember I just saw first computer in 1992 that was all based on 486 microprocessor, or it is a 32-bit.
Okay, so how
जो ये आर्किटेक्चर यूज करता है और सॉफ्टवेयर स्टैक यूज करता है उसको हम 8x86 बोलते हैं, और अदरवाइज दैट इज 64-bit.
Sir, how can we interface this SDK 86 with Android, sir?
That is basically hardware difference. Like for example, लेता हूँ, जैसे nowadays what happens, we have laptops, right? So laptops are, let us say, they provide 64-bit laptops are there. There's a internal processor is 64-bit. No, जब उसके ऊपर हम कोई you might have experienced, जब उसके ऊपर हम कोई सॉफ्टवेयर इंस्टॉल करते हैं which is 32-bit, वो अपना सेपरेट फोल्डर बनाता है, that is named as x86. अगर हम उसके ऊपर 64-bit सॉफ्टवेयर इंस्टॉल करते हैं वो नॉर्मल इंस्टॉल होता है. Otherwise there are two folders in the 64-bit systems.
One more doubt, sir.
Yes.
What is meant by Dalvik virtual machine, sir? Practically, sir, how can we use that?
Okay. Dalvik virtual machine is similar to the JVM. Java virtual machine क्या करता है? It just provides an environment to the user interface. For example, whenever I play any game, so it provides an environment. वो जो गेम मैं ओपन करता हूँ पीसी पे, वो एक एनवायरनमेंट प्रोवाइड कर देता है मुझे. दैट इज अ जावा वर्चुअल मशीन.
Okay.
So we have just discussed that in very much detail. That is DVM. So that is parallel to JVM. So ये DVM क्या करता है? For example लेता हूँ, जैसे मेरा Windows ऑपरेटिंग सिस्टम क्या करता है? It provides an environment. ये डेस्कटॉप प्रोवाइड करता है, और डेस्कटॉप के ऊपर जो भी मैं एप्लीकेशन खोलता हूँ वो डेस्कटॉप के ऊपर खुलती है. Similarly, so my DVM provides an interface to my Android system. So ये एक टूल प्रोवाइड करता है, ये एक इंटरफेस प्रोवाइड करता है, और उसके बीच में all applications are open and all resources are allocated. The different requirements, applications might have different requirements. तो वो सभी DVM handle करता है. That is a runtime. This is a runtime actually.
Yes, sir. Thank you, sir.
Yes, from other centers, queries from other centers. From JCRC Jaipur. Yes, sir. You have any query? DIT Dehradun.
No, ma'am.
Okay. Then JCDM Sirsa. IET Alwar. Nadran India Engineering College Delhi. IGD TUE.
We have no queries. We are from Northern Engineering College.
Okay.
We have no. Thank you.
Okay. So I thank you, sir. I thank you for this session, and tomorrow again we will have session on PIC microcontrollers and its interfacing with the PIC type of microcontroller. So we will start with our next session tomorrow at 9:30 a.m. sharply. So thank you once again.